you what all I have posted for you online. So when you go to your Canvas course, and I naturally assume you've all read through the Canvas course and know where all these resources are, but right here on the Canvas course, if you go to announcements, I have a special announcement that's just called answer keys for in-class notes. So I'm not going to make lots and lots of announcements with answer keys. I'm just going to keep putting them right in here. So when you click on answer keys, take a look. You have your chapter 1 class notes, and then the answer key, and then the chapter 2 notes, and then the answer key, and then the chapter 17 notes, and then the answer key, and I just put up the practice test solutions. So in other words, if you ever wanted to download another copy of a blank copy of the notes, that's a blank copy of the notes, and then that's the answer key. So I'm sure you're all very excited to look at the practice test solution. So first of all, I don't have any more practice tests. I assume that means everyone took one. Does everyone have a practice test? You need one, Sadia? Golly gee, where did my extra copies go? Who else needs one? David, do you need one? I saw a little confusion on your face. I wonder where on earth my other practice test would have gone to. Well,
Practice test.
oh, well, you know what? I'm just going to post it online. I'll post the practice test online, or I'll email it to you. But I don't see any more copies, so.
Yesterday, or?
Yeah, I had it on the table the other day. So provided you picked up everything I set out for you to pick up, you should have it. David and Sadia, check. Does everyone else have it? Jose, you have it. Michelle, you have it. Luis, you have it. Nani, you have it?
Yeah, I have it.
Oh, yeah.
Oh, you do have it. Okay, David, I bet you have it too. All right. Keep looking there, David. Is that it? All right. Okay, so in any case, folks, there you go. Those are all the answer keys. Now, what's my recommendation? You should take the practice test over and over and do the problems over and over until you can do it. Right? So look at the solutions on the practice test. Make sure you have that skill down, because then when you come in to take the test, you just boom, 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 and you're done. All right. Now, let's review real quick, and then we're going to see the very exciting skill that we're doing today. So let's start with these one more questions. Ultimately, when you solve a system or solve a matrix, what are you finding? When you solve a system or you solve a matrix, which is one and the same, what is it that you're finding? Like, let's say that I have a system, either a simple system like this, or if I have some sort of matrix, and the matrix looks like this.
Finding coordinates?
Yeah, you're finding a coordinate, right? You're finding a coordinate in space. Now, when I say we're finding a coordinate in space, what typically is happening at that coordinate? It's an intersection point of two lines. So if we're looking at a two-variable, two equation, and the solution is a point in space, and that point in space is the point of intersection of those two lines. Okay. What is a multivariable function? Just kind of what is it? Like you describe it to anybody standing. Yeah, there's more than one variable, right? So instead of something like f of x equals 3x minus 2, which is a linear equation, that's a line, just like all these are lines. And instead of a single variable, you would have a two-variable equation. And then you'd have something like maybe 4x squared minus 3y and plus 3. And now you say, well, what does that mean? And what that means is that you take the xy plane that was flat on the board. Okay, so I want you to imagine the xy plane is flat on the board right here, and that's two-dimensional space. Now, what if we take the xy plane and lay it down flat on a table? So now my xy plane is sitting here like this. Does that look like the xy plane is sitting flat on the table? And now I have a z-axis poking out the top that measures how tall off the table we are. So when you have a multivariable function, it's now as if, so everybody, I want you to memorize this with me. The y-axis is running this way. That should make sense to all of you, because if you're looking this way, the y-axis would go like this on the ground, and then the x-axis will go this way. And so anytime you plug a value in for f of xy and you calculate it, that value is telling you now how far off the floor you are. Okay? So when we have a multivariable function, the xy plane is now on the ground, and whatever value you get out of it is now telling you the height of how tall you are. And so climbing a mountain or thinking about a mountain is the best analogy. So In all of our examples today, let's keep in mind that there's a mountain right up here. Okay, like there's a mountain, well, a small hill. Really, it's a dirt pile. Okay, but there's a mountain right here. And that's the y-axis, and this is the x-axis. And when you plug in your two values for x and y, it's calculating a height of how high you are on that hill right now. So what kind of, okay, well, so first of all, that's what a multivariable function is. So you're now plugging in at least two values, and the value you're calculating is the height above the ground. Okay. So what does a multivariable function look like? Well, I just kind of described it, but what does it look like? Yes, 3D, and it essentially looks like a, like a mountain or a mound or a hill, or it looks like something. Here are some pictures. It could be any of these, right? So like the cow. Yeah, the cow. Okay, so this is a really nice multivariable function. It's really nice because you can tell that there are some values where it's taller than ground level. Okay, it's rotating. Now we can't see anything. Stop rotating. So there are some values where you plug in x and y and it's tall up off the ground. And other values you plug in for x and y and it goes below ground level, negative values of height. So that's what a multivariable function is going to look like. It could look something like this. And this is what is called a saddle. Does it look like a horse saddle? Yeah. Boy, these things keep animating themselves. Okay, now look. Now that the gray's gone. Does that look like a saddle? You'd hop onto a horse and you'd have your legs going down one way and then you got the saddle in front behind you. That's called a saddle point. And you'll notice that point right there, it's like a little flat spot where you're, boy, I wish that wouldn't do that. Here's another saddle. No animations. Okay, there. So this one, if you were sitting right flat, that's where you're going to sit on the saddle. And so in the, let's just call this the y direction. In the y direction, you're going uphill in front and behind you. That makes sense. When you're sitting on the saddle, it goes up in front of you and it goes up and behind you, right? So that's a positive slope. Whereas your legs, those have a negative slope on either side because your legs are going down. It'd be a little awkward if you turned and sat the other way. You'd be doing like the splits or something. That would not be comfortable. So a saddle point is unique because in one direction, it's a parabola facing down for your legs. But in the other direction, it's a parabola facing up to keep you in the saddle. So that's a very unique point. Is that a maximum or a minimum? You could say both. It's the minimum of this parabola. It's the maximum of that parabola. A saddle point is neither a maximum or a minimum. We should all be okay with that because remember, in two-dimensional calculus, you've got a facing up parabola, and this is a minimum. You've got a facing down parabola, and this is a maximum. But remember, we also have these, where it's flat, the slope is 0, but is it a maximum or a minimum? Neither. And so a saddle is the two-dimensional example of a transition point, where it's not a maximum, it's not a minimum, it's both simultaneously. That point appears to be the maximum of that curve, but that point appears to be the minimum of that curve. You could call that a two-dimensional saddle. But we should just call this a three-dimensional saddle. Okay, so a saddle point is very interesting and unique. We want to be mindful of the existence of a saddle point. But typically, a graph is either going to have a maximum. So my multivariable three-dimensional graph will have a maximum like that. Or you would have a minimum. So where's a graph? Well, this graph. This graph obviously has a minimum value. Now let's look at this one real quick. The minimum value. How do you know that it's a minimum? How do you know that it's the minimum? What characteristic? What?
This graph is going down.
Well, the graph goes down, 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 and then that's as far down as it goes, and then it goes back up. Sure, that's minimum. What unique trait does a minimum point have? Like if you're right here, what's the slope? Yeah, and if you're over here, what's the slope? Yeah, I mean, I suppose it depends on your perspective. Over here, this is a positive slope, and over here, there's a negative slope. But if you're at the bitty bottom, what's the slope? 0. 0. So as always, that's the characteristic that the minimum of a three-dimensional graph has, is that at that point, the slope is 0. Much like here, at the minimum value, the slope is 0. So in all calculus classes, you're always looking for a slope of 0. You're always looking to set f prime of x equal to 0, because that's finding where the slope is 0, and therefore you're either finding a minimum, a maximum, or a transition point. or a minimum, a maximum, or a saddle point. Okay, one more thing. We can only calculate slope in either the, here remember, here's my y-axis and here's my x-axis. We can only calculate slopes in one of those two directions. So if I want to, I can calculate the slope in the y direction. And so, you know, again, imagine my hill right here, okay? Then I could have that in the y direction, there's a slope going uphill, but then over here, it could be in the y direction, now I have a slope going downhill. Now imagine, again, you've got the x-axis. I could be over here, and I've got a slope going uphill, the mountain, and then as soon as I get over here, I get a slope that's going downhill, the mountain. Of course, it all depends on which way you're facing and where your eyeballs are. So the key thing is that if you want a real minimum, then that means that simultaneously, you need to have in the y direction, the slope is 0, and in the x direction, the slope is 0. Right? Does that make sense? The true bottom, you need to have both the x and the y derivative being 0. Because if the y derivative was 0, but the x derivative was 0, that wouldn't be a flat spot. Right? You'd still be on the hill, and because you'd be sloping down that way. You know, if you put a marble on my arm right now, it would definitely roll that way. It wouldn't roll this way at all, but it would still roll down the hill. So you're not at a minimum yet. But if both the x derivative and the y derivative are both 0, then that's a genuine flat spot. Okay, so these are some main ideas that we want to talk about today. Let's just kind of summarize that real quick. On a 3D graph, which again is kind of tough to draw. There's my x-axis, there's my y-axis, there's my z-axis. If I have a paraboloid, which is that fella. There, can everyone tell that that's a real nice 3D drawing of a paraboloid? Can we all kind of pretend? So to find a maximum value right there, then that means that the derivative in the x direction is equal to 0. So watch how I write that. F little x will be equal to 0. And the derivative in the y direction would also have to be 0. So in order to have a genuine flat spot, you would need to have both the derivative with respect to x be 0 and the derivative with respect to y be 0. And if you do know that both of those derivatives are equal to 0, you know you have a flat spot. You just don't know yet if your flat spot is a maximum or a minimum. There, does that look like a minimum? Or it could be a saddle. And my goodness, I have no idea how to draw a saddle. Does that look like a saddle? Yeah, it looks scary. I'm sorry to ruin your dreams tonight. So then that would be a saddle point, right? So we have a saddle point, we have a minimum, we have a maximum. In all three cases, the derivative with respect to x is 0, the derivative with respect to y is 0. So the only thing is that if we're doing work by hand, and we have not yet looked at a graph, and all we know is that the derivative in both directions is 0, we don't know yet if it's a max, min, or a saddle. We would have to do more work. And how do we typically find out if something is a maximum or a minimum? Like let's say we're just working in 2D. I'm working in 2D, and I found out that this right here is a flat spot. How do I know if it's concave up or concave down or a transition point? What do I have to calculate? The second derivative, right? Remember, we do the second derivative. Only when you calculate the second derivative, then you can say that if the second derivative is positive, then that's concave up. Whereas if the second derivative is negative, it's concave down. Whereas if the second derivative is equal to 0, well then that means it's not concave up or concave down. Right? Yeah. Okay. Well, so this is what we're going to do today. We're going to apply the things that we learned in calculus to the three-dimensional case. And that's the really exciting thing we're doing today. Multivariable function. You'll be able to find the flat spots and then tell me if it's a minimum or a maximum or if it's a saddle. You want to put that on your resume, don't you? Like resume, years experience, I can take a multivariable function and find the flat spots and determine if it's a max, a min, or a saddle. Whoa. Don't just put that on your resume, put that on your eHarmony page, right? Am I right? Okay. So, What's next? What does a multivariable function look like? It's a 3D graph. How do you take the derivative of a multivariable function? We're about to review that. And what are we interested in finding when we look at a multivariable function? Oh yeah, the 3 features. We're looking for a max, a min, or a saddle. Okay, so everybody, let's do it. I'm super excited to do this with you. It's a really sophisticated idea. I need to tell you. Everybody go ahead and flip to 17.2. I think that's where we roughly left off. And did I already tell you what did one nut say to the other nut? Oh my. I have no hope of telling you a joke. Yes, I do. While you guys are getting out your papers, I will find a joke. We did that one. Yeah, I think we did a couple of these. What number did we stop at? 11. All right, as in we didn't do 11? No. Okay, great. Okay, this will be fun. Oh, how many apples grow on a tree? All of them. Oh, that's funny. Oh, this is a good one. This is a good one. You're going to love this. I just watched a program about beavers. It was the best damn program I've ever seen. That is a good one. Okay, speaking of which, here's another good one I've never told. Over the weekend, I went to a zoo that only had dogs. It was a Shih Tzu. A Shih Tzu? The type of dog, it's a Shih Tzu. I'm going to show everyone a Shih Tzu, just so you know I'm not sitting here swearing. I would not use potty words in class. Shih Tzu. There we go. That's a little Shih Tzu.
So only outside of class?
No, not even then, because I have children. My wife and I had to agree we're not allowed to use potty language anymore. All right. So, folks, everyone's ready? Let's do it. Now, we're about to find second-order partial derivatives. Now, what does second-order partial derivatives means? It just means the second derivative. And just like the second derivative of a single variable meant concavity, well, the second derivative of a multivariable function also means concavity. All right? It's universal. It doesn't matter if it's single variables or not. In a multivariable function, f of x, y still means height. And if I do the derivative, so f with respect to x, for instance, that still means slope. And if I take the second derivative with respect to x, that still means concavity. So isn't that nice that as you switch from single variable functions over to multivariable functions, everything still has the same meaning. The function is the height above the ground, the first derivative is the slope, and the second derivative is the concavity. Okay, so when you do two derivatives in a row, here's the mind-bending part, you could actually do the first derivative with respect to x, and then the second derivative with respect to y. Like why you wouldn't do both derivatives in a row, both with respect to x, you could. In fact, everybody just go ahead. I think that'd make more sense to start that. Look at the next page, number 13, 14. This probably makes the most sense. We're taking the derivative of the function with respect to x, and then we're taking the second derivative also with respect to x. That would make sense, and we can all understand what that means. The first derivative with respect to x is the slope in the x direction. So again, remember, my x-axis is going this way. So that's the slope in the x direction. And if I take the second derivative with respect to x, that's now telling me the concavity in the x direction. Okay? So let's do this one. We're going to take the second derivative with respect to x of this expression. So everyone write it down yourself. F of x times y equal to 8x cubed y minus 7y squared plus 2x. And we're going to find two derivatives in a row. So the first derivative will be with respect to x. So you write f little x of x comma y. And so now, again, remember, we're only treating x as a variable, and we're treating y like a constant, which comes along for the ride. So when I take the derivative of 8x cubed, I'm just going to temporarily cover up y, so I'm not influenced by it. But what's the derivative of 8x cubed?
24.
24x squared. And then the y comes along for the ride. Okay. Now I'm taking the derivative of negative 7y squared. Here, y is just a constant. So this whole thing is just a constant. And the derivative of a constant is 0. And now here I'm taking with respect to x again. So x is a variable. The derivative of 2x is 2. So there's our first derivative with respect to x. But we want to go one step beyond that. We want to find the concavity in the x direction. We're finding the concavity in the x direction. So now we take the derivative again, f little x little x. Notice how that looks different. In a single variable, we would have just written f double prime. Right? In a single variable, we'd write f double prime. Here we're writing f double x. And that means the second derivative, which is concavity. Okay, let's do it again. So with respect to x, again, I'm going to cover up the y. What's the derivative of 24x squared?
48.
Or 48x. And then the y comes along for the ride. And the derivative of 2 is nothing. So there we go, we did it. That expression right there, 48xy, is telling us the concavity of this function in the x direction. Now keep in mind, like if you had a saddle point, concavity in the x direction has nothing to do with concavity in the y direction. So can you imagine, what if I had a function, and here I'm doing the concavity is up in the x direction, and again, here's my x-axis. Whereas I could have the concavity in the y direction being concave down. And if I did do concave up in one direction, concave down in the other direction, what's that special point called? If you got concave up in one direction and concave down in the other direction? A saddle point. That would be a saddle point, right? Whereas if I had concave up in this direction and concave up in this direction, what would that be? A minimum. Whereas if I had concave down in this direction and concave down in this direction, that would be a maximum. Okay? So finding second derivative is really important because it allows us to figure this out. Okay, let's do the next one. We're going to find the second derivative with respect to y for this function right here. So I'm going to start by writing it down in my own handwriting. F of x colon y is equal to 8x cubed y minus 7y squared plus 2x. Anybody notice anything about that function? It's identical to the one we just did. But now we're going to take the derivative with respect to y twice. Should we get the same answer? No. There's no reason to expect that we'd get the same answer, because slope in the x direction has nothing to do with slope in the y direction, and concavity in the x direction has nothing to do with concavity in the y direction. So they're totally independent. So we'll do the first derivative with respect to y. So if y is my variable, then and now I can cover up the x cubed. What's the derivative of 8y? 8. Just 8. And the x cubed comes along for the ride. And then if y is my variable, what's the derivative of 7y squared? 14y. And if y is my variable, x is just a constant, so this is just 2. So the derivative of 2 is 0. So that term goes away. Okay, we did it. That's the first derivative of the function with respect to y. So we just found the slope in the y direction. But now we'd like to go one more step and find concavity in the y direction. So we'll take another derivative with respect to y again. And again, it's very helpful to just temporarily cover up the x. What's the derivative of 8? 0. That's 0. It's nothing, right? It's just a number. So that term goes away. With respect to y, what's the derivative of 14y? 14. It's just 14. So look at that. The answer is just strictly negative 14. When we did the second derivative with respect to x in the x direction, the concavity was still a function of two variables. That the concavity actually depended on where you were. Whereas when you take the second derivative with respect to y, no matter what coordinate you're at, I don't care where you are, the slope is always going to be a negative slope. That's pretty interesting. But no matter where you are on the mountain in the y direction, it's downhill. Okie doke. Well, there we go. We just did it. We did the second derivative with respect to x twice in a row and with respect to y twice in a row. So now what do we want to do? Let's go back and let's try the derivative first with respect to x, then with respect to y. What's up?
When we do the same in number 12 for derivative of x, we wish to still get the negative concavity for the second derivative.
What now?
Number 12, yeah.
Number 14.
Number 14.
Yeah, what about it?
We are doing in terms of y here. What if we do in terms of x? Do
Oh.
we still get the negative concavity, or?
You mean what if you did first derivative with respect to y and then the second derivative with respect to x?
No, again,
Well, this is what we did up here. This is the same function. So this was us doing
It's
x
just
squared.
the same concept.
Yeah, it's the same function. So that's what makes it so interesting. That definitely the result of doing the second derivative in the x direction and the y direction is different. It could be the same. You know, if it's a perfect paraboloid, it would be the same in both directions. But if the shape is not symmetric, then it won't be the same in both directions.
So would it be like a saddle or what kind of curve?
I mean, this could be a saddle. Oh, great question. Graph it. Same old answer to every question I ever ask. Graph it. So, Bata, are you on the edge of your seat to know what this looks like?
Yes.
You go to GeoGebra 3D. GeoGebra 3D, right? That's how we look things up. So here we go. We're going to graph 8x cubed times y
Yeah,
minus 7y squared plus 2x. Okay, so the question was, what does this look like? So first, let me zoom in a little bit. That's the first thought about what it looks like. So I hope you can all imagine that this is like some close-up shot of like a mountain in the Himalayas, right? We're just looking at some interesting mountain. So if I zoom out a little bit, maybe it'll give us some more, oh, there we go. That's a little more detail. And that's what the mountain looks like. Again, we can only see part of the mountain at any given time. But you can tell that this mountain, first of all, do we have a saddle point? Right there. That's a saddle point. Because when you look in front of it, there, it's a saddle point because you're going up that way and you're going up that way. But as soon as you turn it this way, you realize that you could sit down on that like a pair of pants or a horse saddle. So that point is definitely a saddle point, Bata. Does that answer your question?
Yes.
Okay. So what does the graph look like? You can always just look it up. Okay, no. Think about it. Everyone go back to the previous screen. 11 and 12. Here, we're exploring the fact that you can take the derivative of x, then y, or you can take the derivative of y, then x. And so you'll notice again, we're doing the exact same function we just did. Except we're going to do x, then y, and here we're going to do y, then x. And you'll notice I gave you a note. F of x, y means to do x first, then y. So you literally read left to right, just like normal English. Or, you know, normal reading. Okay, so let's take the first derivative with respect to x. Well, you all already have that result on your paper. If you turn it over, you can see what the result was for f little x. I'm just going to go ahead and do it. It'd be 24x squared y plus 2. Is that the first derivative with respect to x? No. Now we'll do the second derivative with respect to y. So now y is the variable, and x is just a constant. So if I treat y as the variable, my x squared is a constant. What's the derivative of 24y? There's 24. So it's 24x squared. And the derivative of 2 is always going to be 0. The derivative of a constant is always 0. So there, that's my second order derivative, first x, then y. Is this a different answer than anything we got before?
Yeah.
Yeah, it doesn't match either of the two answers from before. Okay, now let's try it again, but this time we'll do the first derivative with respect to y. And again, if you turn your paper over, you already have that result. So it's 8x cubed minus 14y, right? So that's the first derivative with respect to y. But now we're going to do the second derivative with respect to x. Does anyone have a guess about what's going to happen? Should we get the same answer or a different answer?
Different.
Yeah, maybe you'd expect a different answer because that's what happened on the other side. Well, let's try it. With respect to x now, this would be 24x squared. And with respect to x, y is a constant, the derivative of 14 is 0, so that term goes away, that's 24x squared. What do we notice? What is f little xy compared to f little yx?
The same.
They're the same. And that will happen provided, so fxy equals fyx, provided f is continuous. So provided f is a continuous function, which, you know, we normally deal with continuous functions, then f little xy will always equal f little yx. Which is nice, because does it matter which order you do it in? If you're going to do a second order partial derivative with x and then y, you can go in either order. Okay. So that's our tools under our belt, folks. Now we have some tools, and we're able to now do some interesting problems. Oh, this is so fun. Oh, it's palpable. Can you taste it? Can you taste the fun, Simone? Oh, good. You were literally taking a bite right there, so you really could taste it. All right. So imagine what we're about to do now. It says, here's a function, a multivariable function, x cubed minus 4xy plus 8y, and we want to find the values of x and y such that both the derivative in the x direction, so remember that's this direction, the derivative in the x direction is 0, so we're looking for a flat spot in the x direction, and we're looking for the first derivative with respect to y is 0, we're looking for a flat spot in the y direction. Not just are we looking for any old flat spot in the x direction, and any old flat spot in the y direction, which could be like that. We're looking for when the coordinate in space where it's flat in the x direction and it's flat in the y direction. Because that's either going to give us a maximum or a minimum or a saddle point. But it has to be flat in both directions. So, first question is, what are you wondering about that function? And you see me walking over to my computer, therefore the question is, what does it look like? Right, what does that function look like? Well, let's find out. X cubed minus 4xy plus 8y. Ooh! Look at this little fella. What do we have going on here? Kind of crazy looking, right? Oh no. There we go. Do you see any maximums or minimums or saddles? Yeah, we definitely have a saddle point though. In here, I'm going to flip it straight this way. Where's the saddle point? Right in the middle. Can you all see it? The saddle point is not right in the middle. The z-axis has no saddle point. You can tell the blue line is the z-axis. That's not where the saddle point is. Where's the saddle point? Right there. Can you see that it's right there? I'm going to rotate it again. Follow the saddle point with your eyes. The saddle point appears to be around the coordinate 2, 3. So if I look at the red axis, it's at the 2. On the green axis, it's about a 3. So we're predicting that there's a coordinate space where I don't know which is red and which is green, x or y. But around the coordinate 2, 3, the derivative in both directions is equal to 0. So that's what the graph is implying. Okay, so let's try it out. That's our guess. So we need to find the derivative with respect to x, and then separately we need to find the derivative with respect to y. So you have a lot of space here. So let's do the derivative with respect to x on the left. What's the derivative with respect to x on the left? Who would like to do this one for us? Sadia. Take the derivative with respect to x. What's the derivative of x cubed? Yeah, 3x squared. What's the derivative with respect to x? Remember, just cover up the y. What's the derivative of 4x? 4, so minus 4y. Y comes along for the ride. And then the derivative of 8 is just 0. So that term goes away. Okay, so far that's what we have. The derivative with respect to x is equal to 3x squared minus 4y. And we want to know, when is that equal to 0? So you go ahead and write 0. And that's one equation that we're solving. When is the first derivative with respect to x equal to 0? So notice, we're about to find a flat spot in the x direction. Direction. Okay? So before we move on, because we can't actually solve that equation right now. There's 2 variables in one equation. You can't solve 2 variables in one equation. If you have 2 variables, you need 2 equations and 2 variables in order to solve it. So now let's go do our other one. So what's the first derivative with respect to y? Diego, take it away. What's the derivative of x cubed?
0.
Just 0. That goes away. What's the derivative of negative 4y?
Negative 4.
Yeah, so just negative 4 and the x comes along for the ride. And what's the derivative of 8y?
8.
Yeah, just 8. So now we're asking, when is that derivative equal to 0? So now we're saying in the y direction, when is the y direction have a slope equal to 0? So that's a flat spot in y direction. All right, well, this is good news, because can we solve that second equation?
Yeah.
Yeah, we can actually solve the second equation. That's very simple algebra. Negative 4x plus 8 equals 0. Move the 8 over. Divide off the negative 4, and we get x equals 2. Well, that's relief, because isn't that exactly what we saw on the graph, that one of the coordinates was a 2? The saddle, the red coordinate was a 2. So far so good. We are hunting down this saddle point right now. So now that we know what x is, can we go back and solve for y? We know x is 2, so now we can bring it over to here and say 3 something squared minus 4y is equal to 0. So then we get to plug in the 2. And we have 2 squared is 4 times 3 is 12 minus 4y equals 0. Move the 4y over, 12 equals 4y. Divide up 4y equals 3. Oh my goodness. Wasn't the other coordinate a 3? So did we do it? Did we find the saddle point from the graph? Yes, we did. Yes, we did. So what we would say now is, and write it out with me, at the coordinate 2, 3, the function f of x comma y is flat in both direction. Conceptually, how does everyone feel about that? Good. Thank you, Don, for responding. Yeah, I mean, that's what we just did. We took first derivatives, which means slope. We set both of those slopes equal to 0, meaning we found a flat spot in the x direction, a flat spot in the y direction. And so now what we know for sure is that that is a critical point. And it's either a maximum or a minimum or a saddle. But if we didn't look at the graph, right now we would have no idea which is which. If we wanted to know which was which, what would we have to do? Well, one answer is graph it, or by hand, what would we have to do? The second derivative. We would have to take the second derivative to see what's what. Okay, everybody, let's try the next one. So we're going to take the first derivative with respect to x. So who's next? Luis? With respect to x, what's the derivative of x squared?
Just x.
No, 2x.
Oh, okay.
And then with respect to x, remember y is just a constant, so the derivative of x is 1, so that's 1y. Derivative of a constant, since y is a constant.
Oh, so it just goes down?
Yep, just 0. It's just 0. Just like the derivative of 5 would be 0.
Oh, okay.
The derivative of 2 is going to be 0. The derivative of y squared, since we're saying y is a constant, is 0. So then what's the derivative of negative 3x?
Negative.
Yeah, negative 3. And the derivative of 2? 0. Okay, there's our first derivative, folks. We set it equal to 0, and we box it, and we say, well, here's one equation that we have. Again, notice this is one equation in 2 variables. We cannot solve it yet. So we have to move on over and do the second or the first derivative with respect to y. So, Simone! How's it in Simoneville over there today? Oh no, Simone. Well, it's about to get better because you're about to take the first partial derivative with respect to y. So what's the derivative of x squared, Simone? Since that's just a constant. Nothing, 0. What's the derivative of, so we're taking the derivative with respect to y, so I'm going to cover up x. What's the derivative of 1y?
I don't know. Is it just?
Yeah, 1. So x comes along for the right, so that's 1x. What's the derivative of y squared with respect to y?
2.
Yeah, 2y. And then what's the derivative of negative 3, since x is a constant?
Nothing.
Nothing. And the derivative of 2? Nothing. All right, folks, so check it out. Now notice, this problem is super duper. Because just doing the calculus, we're not done. All we did was the first derivative with respect to x and the first derivative with respect to y. Now, what do we have to solve?
For one, x or y.
You have to solve a system, right? Which is how we started in chapter 2, was talking about solving systems. So here we just have a system. So I'm going to make myself some space because I'm so low on the bottom of the board. I know that it's hard to see when you're in the back there. I'm going to move my system over to here. Just going to erase all that. Since we now know that we're either talking about a max, a min, or a saddle point. So now how do we solve a system? What would be your choice? I have 2x plus 1y equals 3. Is that okay with everyone? I just moved the 3 over to the right.
I just moved the 3 to the right.
So that's a negative 3. I've added 3 to both sides. Now I have that. And then my other equation is 1x plus 2y equals 0. Out of all the methods in the whole world that you have available to you, what would be the easiest way to solve this system? Would you want to use a matrix manipulation, an inverse, a determinant, substitution, elimination, graphing? Simone, what'd you say?
I said one plus one by two.
Absolutely, folks. I think the easiest way is just to do elimination. After all the fancy stuff we learned, elimination is the easiest. Simone, I feel like I'm missing a joke that you told.
No, I didn't, because I was like half confident.
Yeah. Oh, yeah. No, you're totally right. Elimination is the easiest way to go. I mean, just think. After everything we've already learned, elimination is the easiest. So now negative 2x, no, negative 4x.
Minus 2y.
Negative 4x minus 2y equals negative 6. Now I can add those two equations together. The positive 2y and negative 2y cancel out. We have negative 3x equals negative 6.
X
And-
equals 2.
Yep. And x equals 2.
And we just plug in 2 to one of the equations.
Right. So all that told us now so far is x is 2. We still have to plug that into something. I think the easiest equation to plug that into would be 1x plus 2y equals 0. So now we plug x equals 2 into this. So therefore we have 2 plus 2y equals 0. So moving the 2 over, we have 2y equals negative 2, which means y is equal to negative 1. So what does this mean?
At the coordinate 2, negative 1, there is a flat.
Absolutely. At the coordinate 2, negative 1, the function is flat in both the x and y direction. The function is flat. Y direction. Now, folks, this is really interesting. Just think, when we did single variable functions and you wanted to find a flat spot, what was your process? You just took the derivative and
Solved it.
set it equal to 0. Right? That's how you find a flat spot in single variable calculus. Take the derivative, set it equal to 0. When we're in 2 variable calculus, what do? You have to take 2 different derivatives and set both of them equal to 0, and then solve a system in order to find it. Right? Like going from 1 variable to 2 variables, the work didn't just get twice as much. You now took a first derivative and another first derivative, set them both equal to 0, so that's 2 steps instead of 1. And then you had to take both of those equations and solve a system to get the actual solution. So it is a little more work than what you would do in a single variable case. How's everybody feeling so far? Michelle's saying, this is exciting. Okay. Well, folks, from the big bird's eye view, this is what you can expect, is that you're going to take a first derivative, another first derivative, it's going to generate 2 different equations, and then those equations have to be solved as a system where you can either use elimination, substitution, matrix methods, inverse, determinant, whatever you want to use.
Can we try the next problem by ourselves?
Yeah, absolutely. So there you go, folks. Number 17. Give it a shot. You can work with your neighbor. I'm checking my answer key. Oh, no. Simone, I literally wrote down, this one's tricky.
Oh, okay. Not let her know.
Yeah. In fact, folks, I was going to say we can skip this one.
Oh, great.
Everyone cross it out. Cross out 17. Because we still have plenty more problems to do. And they're all just going to get better. But Simone, you can try number 18 on your own. So everybody, let's try number 18 on your own. It's a really exciting problem because it's a word problem. But keep in mind, it's the exact same process. So you notice, suppose the manufacturing cost of a precision instrument is approximated by m. So now it's m of xy instead of f of xy, but it's still just a function. And what does this measure? The cost. I think it's unfortunate they chose the letter m. What letter should they have chosen?
C.
C, because it's the cost. So you have a function, and x is the cost of the materials, and y is the cost of the labor. So notice that's very interesting. You're manufacturing something. You not only have to pay the people who work for you. It's such a pain. You have to pay the people. Gosh. But you also have to pay for the materials that you bought, right? So that's why you have a variable x and a variable y. So all they're asking you to do is take the first derivative with respect to x and then plug in 3 and 4. So you're not even setting it equal to 0 and solving. Just take the first derivative with respect to x and then plug in 3 for x and 4 for y and see what you get. Everybody go ahead.
Now I'm scared.
You can do it. Tom?
We're just plugging 3 and 4 into the problem.
Folks, just to clarify, you're not just plugging in 3 and 4.
Yes.
Notice, this is the function itself. This is the function with the derivative of the function with respect to x. First, take the derivative with respect to x, then plug in 3 and 4. If you plug in 3 and 4 right now, you're literally going to just find the manufacturing cost. But after you take the derivative with respect to x and plug in 3 and 4, you're finding the slope of the manufacturing cost in the x direction, which is totally different. So take the derivative first with respect to x, holding y as a constant, then plug in 3 and 4. If you just plug 3 and 4 in directly, that's fine. You found out something interesting. You found out the cost. See, Bill?
Okay. You say, what did you say? I got it. So terms of x, right? Is it right?
There you got it. Well, the y comes along to the right.
Okay.
And you don't have to write 0. So.
I know, it's just.
But yeah, no, that's fine. I appreciate that. If you like to write the 0, that's totally fine.
And what do you mean by
It's
put
just
mx?
There's no X.
in this? What do you
Well,
mean?
now you're going to plug in 3 and 4. The problem says plug 3 and 4.
Okay, so
It's
just
negative
x.
9y. because
No.
we're-
Oh,
Plug in 3 for x, 4 for y.
okay.
I think I got it right.
That's x, y. So 3, 4 is x, y.
Okay.
Yeah.
No, you got it. That's good. How'd it go, David? You got the 20x minus 9y. You got 24. Okay, good.
Oh, that's what I got.
20. Oh yeah, 20x minus 9y. And now it's plug in 3 and 4. You plug in 3 for x, 4 for y. So you can plug in 4 right there for y. Yeah, you're almost there, about that. You're doing it correctly. Yeah. You almost got it there. That's how they use it. This is great. You even did the derivative with respect to y. You didn't have to do that, but I like that you did. It's good practice. You're just doing this one and then plugging in 3 and 4 into that equation. You can feel free to solve this one as well if you like. Yeah, 20x minus the y comes along to the right.
So then when you get that, of the, mx, 3, 4,
Yeah, well here, let me just catch up with y'all. So the first derivative with respect to x, I think, walking around the room, I think just about everybody had 20x, the middle term goes away, and then this last term is just minus 9y. Right, so what does this thing represent? The slope in the x direction. Right? So that expression that you just calculated is the slope in the x direction. So now they're saying, at the coordinate 3, 4. So in particular, if you go stand at the coordinate 3, 4, what is the slope in the x direction? So you plug in 3 for x and 4 for y, and you get 60 minus 36, which is 24. Now go one step further, folks. This is a slope. So what do I do to my number 24? Over 1. So now what are we saying? We're saying that the 24 is the value of M, so that's $24 in cost. And the denominator, we just took the derivative with respect to X. What does X represent again?
Material.
We have a cost of material. So that what we're saying is that the change in the manufacturing cost is $24 for every one more unit of material that you buy. So if you're already at 3-4, that is 3 units of material and 4 people that you're paying, then how much will it cost you to buy one more unit of material?
$24.
$24. So this is a very interesting solution that we found. That depending on how many units of material and people you already have working for you, you can calculate the slope of that, and that will tell you how much money you have to pay for one more unit of material. Now, I saw Sarai go ahead and calculate in the y direction. Let's look at that. M sub y, and so in the y direction, that would be what? Nothing, and then 100y, and then minus 9x. Sarai, is that what you got? Yeah, so now let's look. Now we're saying the slope in the y direction, if I plug in 3, so check this out, that would be 300 minus 36, which is now 264. So look at that slope. That means that now, again, if you already have 3 units of material and 4 people working for you, then how does your manufacturing cost change with every one more person? How much does one more person cost you? $264. So see, that's the 2 things that we just found out. Now, who calculated the actual original cost? Luis, what was it? If you plugged in 3 and 4 to the original?
Oh, I didn't.
But did anyone plug 3 and 4 into the original?
Oh, you stopped us.
Okay. Well, let's find out. Because now that'll really help round out this solution. If I simply calculate the overall cost of 3 units of material and 4 people, then that's going to be 10 times 3 squared plus 50 times 4 squared minus 9 times 4 times 3. I got a syntax error. Damn it. Oh, just plus. There you go. I got 782. Okay? So everybody, now look, see, now that we've plugged a whole lot of things in, we can really tell a whole story. Okay? So when I bought 3 units of material, which could be whatever, you know, metal, paper, wood, and 4 people are working for me, then my manufacturing cost is $784. Second of all, if I buy 1 more unit of material, it'll cost me 24 bucks. If I hire 1 more person, it'll cost me 264 bucks. That's the whole story that we just told. Isn't that interesting? That's interesting. That's really important. If you're analyzing a business and you're a consultant for a business, you can get all that information for them just by taking a derivative. And you're saying, all right, this is how much you're currently paying. If you want to buy some more material, it's 24 bucks. If you want to hire another person, it's 264. And they'll be like, can't we pay that person less? I'm just kidding. Okay, how does everyone feel about that? All right. See, wasn't that an interesting question? Yeah, that was a really interesting question. All right, folks, here we go. This is the main thing for the day. This is our main skill for the day, and it's all right? This is it. Once we do this skill, we're done with the chapter 17, and then we can just review for the test, right? We'll have a little bit of time today to review for the test. And keep in mind, I already gave you a practice test, and I posted the solutions. So when you come here on Tuesday, you're all going to say, Mr. G, I'm pumped. I'm ready. Give me the test. And I'll say, you have 2 hours and 40 minutes to take that test. And you'll say, I'll be done in an hour. See you later. I'm going to the beach. Is that what you're all going to say?
Yeah.
No. All right. Better, yeah, I'm going to Simonville. Or, yeah, I'm going to work. Okay, so take a look here, folks. Section 17.3, it says relative extrema and saddle points. So first of all, an extrema, what do you think an extrema is?
An extreme diva.
Oh, it could be an extreme diva. It's either a maximum Wait, yeah, it could be that. So that's a maximum, or it could be, what do y'all think of my 3D drawings here? Are you compelled? You're like, wow, Mr. G, forget the algebra. What?
You should teach an art class too.
Oh, yeah, absolutely. Especially when I do something like draw me standing on top of it. The whole world would be like, oh, yeah, we need Mr. G and his drawing genius. Okay, so it could be an extrema, or it could be a saddle point, right? I don't even know how to draw a saddle.
You have to draw the horse first.
Yeah. Maybe some stirrups. Oh, yeah. Oh, no.
It's like a dinosaur.
It's terrible. Oh, that's the worst. So, yeah, or a saddle. It does look like a dinosaur. Oh, man, his mouth isn't even where it should be. All right, so relative extreme and saddle points. First of all, everyone take a look up here. They've got the letter D. Would anyone like to take a wild, wild guess about what D stands for?
These nuts.
Oh.
Definitely don't say that again. No.
Demand?
What? Demand. It could be demand. That's fair because we're talking about
No.
business type problems. Let me remind everybody something. When you do the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a, the quantity b squared minus 4ac had a special name. Because if b squared minus 4ac is positive, then that means that your solution, your parabolic solution had two solutions. If your b squared minus 4ac was 0, that means that your parabola was sitting on the x-axis and there was only one solution. And if your b squared minus 4ac was negative, that meant that your parabola was floating above the axis and you had no solution. So two solutions, one solution, zero solution. I don't know if you remember that from 120 or 150, but the b squared minus 4ac determines whether you have two solutions, one solution, or zero solutions. And you might say, oh, is it the determinant? Because it determines it. But we just saw what a determinant was the other day. The determinant was a matrix idea. That if you had A, B, C, D, the determinant was A, B minus BC. Remember that? That was determinant. This D word is different, even though just like the word determinant has determine as a root, it determines which kind of solution it is. This thing was called the discriminant.
Discrimination.
Yeah, not discrimination. So does anyone remember the word discriminant?
No.
Maybe you do, maybe you don't. Well, D is called discriminant because it discriminates, not against people, but against the type of solutions that you're going to have. Everybody go on up here for D and write discriminant. Discriminant. Discriminant has potentially a negative connotation because it's not good to discriminate against people, right? That's a bad thing. Don't discriminate against people for any reason. But discriminating is a positive thing. Like, I have a discriminating taste when it comes to pizza. I know good pizza from... Oh, you haven't? Oh, to have a discriminating taste? I've often heard that in terms of wine. Like, I have a discriminating taste. This is good wine. This is bad wine. But it could be for anything. You know, like pudding. I have a discriminating taste when it comes to pudding. I know good pudding. I know bad pudding. Okay, so discriminating. You're discriminating between these four situations. So what do we have? If D turns out to be a positive number and the second derivative with respect to x is negative, then that means that we're talking about a maximum point. Now notice, other than the fact that the discriminant being positive doesn't really mean anything to us, if the second derivative is negative, what does that tell you about a normal one-variable equation? If the second derivative is negative, what would that normally tell you about your graph's concavity? It's concave down, and therefore that point is a maximum, right? Okay, so this information right here is pretty much all we need to know. The second derivative is negative, and that means that it's concave down, and therefore it's a maximum. But you do also have to have a positive value of this discriminant thing. Okay. Next, what if the discriminant is positive, and the second derivative with respect to x is positive? That's a minimum. And again, that makes sense. Because if the second derivative with respect to x was positive, then we all know that means concavity is concave up, and therefore that point is a minimum. So what this is basically telling us so far is that we do this long calculation right here for d. D is our discriminant. And provided d is a positive number, then the second derivative with respect to x tells us if it's a max or a min, just like we would expect. Okay, so now what if d is negative? If d is negative, if our discriminant is negative, that means it's a saddle point. Okay, so we're looking at various possibilities here. We do this calculation for d. If d is positive, we either have a maximum or a minimum, and we can tell which. If d is negative, it's a saddle point. And if d equals 0, we have no idea. The test is inconclusive. That test, okay, this thing is not all-knowing. It's only knowing to the extent that if the value is positive or negative, you know you either have a max, a min, or a saddle. If d equals 0, you have no idea. In which case, what would you have to do? If you calculate d as 0, what would you have to do? Graph it, thank you. Yeah, you'd have to graph it, right? Because the algebra won't tell you. All right, so everyone's excited? Let's go calculate d. First, everybody, let's write down d and see what it says. Okay, d is equal to the second derivative with respect to x at a critical point. Okay, so AB is representing a critical point. You know how we just went through that process? Like this one right here. We found our critical point. We found the point in space that was flat. So you still have to go through that whole process of finding your critical point in space. And what they're saying is you would take the second derivative with respect to x at the critical point times the second derivative with respect to y at the critical point minus the second derivative with respect to x then y at the critical point squared. That is how you calculate the determinant. Also, I'm assuming you're laughing at the ridiculousness of the formula. Right, I know. Like
dinosaur too is kind of.
It's what?
A little dinosaur.
Oh yeah, and my dinosaur is really cool. Tail. Some little dinosaur feet. Now come on, this dinosaur foot thing that I just drew, that's probably the best part of my drawing, unless you're like, Mr. G, that's obviously elephant feet.
Why is 1 foot bigger than the other?
Hey man, don't discriminate against his feet. Okay, so everyone understands what this d is? So d is equal to, notice, this isn't a calculation of concavity in the x direction. Let's write it. Concavity in the x direction. Concavity in x direction. This is the concavity in the y direction. And then this is the mixed concavity, where you did one variable and then the other. And that whole thing is evaluated at the flat spot AB, where f little x was equal to 0 and f little y was equal to 0. Okay, so that's what AB represents. It's the flat spot in space that you already must have found by setting the first derivative of x equal to 0 and the second derivative of y equal to 0, solving the system and finding the critical point. That's what we practiced already. We practiced finding a critical point by setting the first derivative with respect to x equal to 0, the second derivative with respect to y equal to 0, solving the system. That's the critical point. So that's your AB. Okay. This is going to be a really fun process, folks. So you don't cross out 20. I'm just removing it from our visual field. And we're going to go ahead and solve number 19. Okay, let's go ahead and solve number 19. Everybody, we're ready. What's the first thing we have to do? We have to find AB. So I'm going to make some steps. First, find flat spot AB by solving f little x equal to 0 and f little y equal to 0. All right, so that's step 1, is we just have to go find our flat spot. Again, we've already done a couple problems like this, so let's do it. First, we take the first derivative with respect to x, So f little x of xy is equal to, so the derivative of x squared is 2x. The derivative of xy, y is a constant, so the derivative of 1x is just 1, and y comes along for the ride. The derivative of y squared is nothing. The derivative of negative 3x is negative 3, and the derivative of 2 is nothing. And I'm going to take that and set it equal to 0. And that's one of my two equations that I have to solve. Keep in mind, we're not doing anything with D yet. Right now, we're just trying to find our coordinate AB. So that's the first derivative with respect to x. Now let's find the first derivative with respect to y. So with respect to y now, the derivative of x squared is nothing. The derivative of xy, since x is a constant, that's really 1y. So the derivative of 1y is 1, and x comes along for the ride, so that's 1x. Derivative of y squared is 2y. Derivative of 3x is nothing, and the derivative of 2 is nothing. And so now I'll set that first derivative equal to 0. This is a gloriously lengthy process. I mean, what feels better at the end of the day than doing a long, multi-step problem and running for an hour on a treadmill? I mean, both of those things sound equally compelling, don't they? Some people tell me they could never run on a treadmill. After 5 minutes, they'd be like, this is so boring. Okay, so now what do? We took the first derivative in terms of x and y. We have two equations and two variables. We have to solve this system. So you can solve the system in whatever way is best for you. So now, I'd say that's the second step, right? Second, solve the system. So we have 2x plus 1y equals 3. Again, I'm just moving the 3 over. And 1x plus 2y equals 0. And Lordy, isn't that the exact same system? No.
Yeah.
Yeah, it is. Yeah, that is the system we just solved a little bit ago. So goody gumdrops for us. We already know now that if we solve that system, our answer is going to be 2, negative 1. So we just lucked out. We can just look at the previous problem and know what the answer was. So keep in mind, folks, that's the value of AB, right? So A is equal to 2, and B is equal to negative 1. How's everybody feeling so far? Okay. Third, now we are ready to start solving this discriminant, which means we need to find the second derivative with respect to x, the second derivative with respect to y, and then we have to do a second order partial derivative of x then y. So let's start with xx. We already know what f of x is. Sorry, f little x. So let's go ahead and find f little x twice, f little x. What's the derivative of this thing with respect to x? The derivative of 2x is
2.
2. The derivative of 1y is
0.
nothing. The derivative of 3 is nothing. So there we go. That's the derivative with respect to x and then x. What about the derivative of y with respect to y? Twice. So now we look at f little y already and take the derivative with respect to y. So the derivative of 1x is nothing. The derivative of 2y is also 2. Now, we need to find the derivative with respect to x, then y. So we already have the derivative with respect to x. So now we're going to do this one with respect to y. So the derivative of 2x is nothing. The derivative of 1y is 1. The derivative of 3 is nothing. So look at what we just came up with. We have our second order partial derivatives for our formula for D. And what you'll notice about these, do any of them have variables in it?
No.
No, they all turn out to be a constant. So is there anywhere for us to plug in the 2 and the negative 1?
No.
No, there's not even a place to plug it in. So this one is just a wildly easy example. So now let's write down our formula for D. D is f little x at 2, negative 1 times f little y at our flat spot, 2, negative 1, minus at 2, negative 1 squared. That's the formula for D. So now all we have to do is just plug in the values. All right, so what was f little x?
2.
It is 2. We don't even have to plug in the 2 and the 1 because the formula was so easy, it didn't even have variables in it. F little y, also 2. F little x, y, just a 1. So what does that give us? 2 times 2 is 4, 1 squared is 1, 4 minus 1 is 3. And therefore, D is equal to 3. Now I want you to notice, we just did all that work to calculate D. And what is D again? What does it stand for? Discriminant. And what are we discriminating between? What kind of flat spot is this? Is this flat spot a maximum? Is it a minimum? Is it a saddle? Or are we inconclusive? So now, let's all go up to the top. Now, by the way, I'm always going to give this to you. You don't have to memorize it. I'm just going to put it right on the test. So D is 3. Therefore, is D positive, negative, or 0? Positive. It's definitely positive, so it's one of these two. And furthermore, what's F little XX? Is F little XX positive or negative? Positive. Positive. So they're both positive. So D is positive, F of XX is positive. Therefore, what are we looking at? A minimum.
Oh, what it's called.
Or what?
Nothing.
So now that we just did all that, what are we all dying to see?
The graph.
A graph. Oh man, who wouldn't want to see the graph, right? I mean, after all that, let's take a look. So the graph was x squared plus xy plus y squared minus 3x plus 2. And, oh, what is it? I mean, yeah, okay, it could be a bullet. The technical name is it could be a bullet. The technical name is a paraboloid. So it's a paraboloid, and sure enough, does it have a maximum or a minimum or a saddle? That's a minimum. And where is the minimum? If I turn it sideways and look straight down at it, where is that minimum? It looks like it's at 1, 2. Were those the numbers we got? The coordinate? 1, 2? Yeah, in fact, sorry, that's flipped around. I need to find my positive numbers. Yeah. It is, in fact, a positive 2 and a negative 1. So we had the coordinate correct. The flat spot was at 2, negative 1. And the flat spot is a minimum. And at that point, you'd say to yourself, wow, all that calculus worked. All the calculus really did tell us that at the coordinate 2, negative 1, there was a minimum. And then you would say, Mr. G, why wouldn't we just graph it? Right? I mean, if you were a business person and you were helping a business as a consultant or a manager, wouldn't you just graph it? Anyone have any opinions about that?
I like to know how to do it.
Well, that's absolutely true, Josue. Thank you for saying that. I did pay Josue to say that. Yeah, no, it is good to know how to do this because this is the actual mathematics behind it. Okay? Good job, folks. You cannot graph this on your TI-82. There is no way. Your TI-82 only does single variable functions. These are multivariable functions. So there's no way to check your work on a graphing calculator. You would need to go to GeoGebra 3D. GeoGebra 3D will tell you. I mean, it'll graph it for you. All right. Well, everybody ready to try that again? Yeah. Boom! Let's try it again. Okay, I'm going to leave that there, and now I'm just going to go ahead and take this other problem. I'm going to write it over here. So let's write our other problem, and I'm going to call on all of you to tell me what to do and when to do it. So we've got a multivariable function, f of x, y, and it's x cubed minus 12x plus y squared. And keep in mind, what does this thing look like? Some sort of a mountain, right? It's some sort of a mountain. You don't know what the mountain looks like. It's got little nooks and craggies, and you know there could be a saddle in there. Who knows? But it looks like something. So what's our first step? Done? What do we do first?
Find a flat spot.
Find flat spots.
My goodness, Adon, your voice has changed. What now, Adon?
Find the flat spots.
Yeah, find the flat spot. And how do we do that, Simone?
Fx equals 0. Is that what you want to know?
Yeah.
Y equals, yeah.
Yeah, set f of x equals 0, set f of 0, f of y equals 0. So, first things first, we need to go ahead and find the first derivative with respect to x. So f sub x of xy. So the derivative would be 3x squared minus 12. Oh, and the y squared goes away. That's a nice, easy equation. Remember setting them both equal to 0 and then solving the system. But the good news is, can we just solve that? There's no y variable in it, so we can just solve it. Check it out. 3x squared equals 12. Divide by 3, x squared equals 4. Square root both sides. X equals 2 or negative 2. I wrote them out separately instead of plus or minus 2 because we now know we have two different flat spots. Right? There are two different flat spots on this graph. Now let's find the first derivative with respect to y. The first derivative with respect to y, x cubed goes away, 12x goes away, and that's just 2y. So we said that equals 0. So remember, this whole first phase, we're looking for flat spots. And in fact, I should write that down. The first thing is to find your flat spots. And you do that by taking the first derivative with respect to x and y, setting both of them equal to 0, saying, hey, in the x direction, when is it flat? Hey, in the y direction, when is it flat? And then solving both of these. So what did we get for y?
0.
It's just 0. So where are our flat spots?
At +2, -2.
Well, as coordinates, the flat spots are 2, 0, and -2, 0. So there are two flat spots. Now keep in mind, what are those two flat spots? Well, they could both be minimums, like udders of a cow. They could both be mountain peaks, like a double-peaked mountain. One could be a maximum and one could be a minimum. Or you could have a saddle point and a maximum, or a saddle point and a minimum, or two saddle points. But we have no idea. We have no idea still what this thing looks like. All we know is that there are two flat spots. Okay, what do we do next? Oh, we already solved the system. Great, moving on. I never wrote third. Third. Now what do we do? Josue, what do we do now? What do we do now?
The second derivative?
Yeah, now we do our second derivatives, right? That's one easy way to think about it. The first thing is you do your first derivatives, and now we're going to do our second derivatives. So find all three second derivatives. All three. Because you're going to do second derivative xx, second derivative yy, second derivative xy. So I'll do f little xx first. What's the derivative of that thing with respect to x?
6x.
Yeah, just 6x. What's the derivative of that thing with respect to y? 2. Yeah, just 2. And then what's the derivative of x now with respect to y? 0. 0. So now again, notice those are simply the equations for f little xx, f little yy, f little xy. Those are the equations. Now when we actually solve the discriminant, we have to plug our flat spots into that before we actually do the discriminant formula. Furthermore, we get to do the discriminant formula twice because the discriminant formula is telling us what is this flat spot, max, min, saddle, I don't know, and then do the discriminant again to say what is this flat spot, max, min, saddle, or I don't know. So we get to do discriminant twice. So let's set this up and write third. Find D of the first flat spot, which is 2, 0. Okay? So let's find D of the flat spot 2, 0. We're going to do that one first. So let's go ahead and start writing D equals, and it's going to be f of xx plugging in 2, 0. Let's write down the whole formula. Times f of yy plugging in 2, 0. Minus f of xy plugging in 2, 0 squared. So what is f little xx if you plug in 2 for x and 0 for y? You plug in 2 for x, 12, and you plug in 0 for y. Yeah, notice there's no way to even plug in the y. There's no y variable. You can't even plug in y. So all we're doing is plugging in x. And yeah, 6 times 2 is 12. So that number is 12. What about f little yy if we plug in 2, 0? Well, first of all, there's no variables. So I can't even plug in the 2. I can't even plug in the 0. What's the answer? Just 2. Last one, again, there's no variables. There's nowhere to plug in the 2 for x and the 0 for y. The answer is simply 0. So what do we have then? 12 times 2 is 24 minus 0 squared is just 24. So D, positive, negative, or 0? Positive. So that means we're either looking at a minimum or a maximum, depending on what our f little xx is. So D is positive. What's f little xx?
Positive.
Also positive. So we're looking at D is positive and f little xx is positive. What are we looking at? A minimum. So the coordinate 2, 0 is a minimum. So you'd say 2, 0 is a minimum. Again, keep in mind, all we've done so far is the discriminant formula for the first flat spot. We still get to do the discriminant formula for the second flat spot. So, well, I'm going to have to write a little small now. So now, find D of negative 2, 0. So we'd say D equals f little xx of negative 2, 0 times f little yy of negative 2, 0 minus f little xy of negative 2, 0 squared. So what is f little xx if you plug in negative 2 for x? Yeah, now this is negative 12. And what is f little yy? Well, there's no variables. There's nowhere to plug that information in, so the answer is just 2. Same thing for the last one. There's no variables, so you can't plug anything in. It's just 0. So what does that tell us? Negative 12 times 2 is negative 24 minus 0. Still negative 24. What is D? Positive, negative, or 0? And now D is negative. Saddle. Yeah, my goodness. That means D is negative, so it's a saddle point. So now we're going to say negative 2, 0 is a saddle. Folks, what we just did is super cool. Right? I mean, you're all on the edge of your seat to see what this graph looks like, right? You're literally on the edge of your seat. Everyone get on the edge of your seat. Scoot forward. Scoot forward onto the edge of your seat, but do not fall off. Plus y squared. Let's look. Oh my goodness. Oh my goodness. Folks, first of all, do you see the minimum down there? Do you see this fella right here looks like an icicle or something from a cave? Is that a max or a min? That's our min. And let's turn the graph sideways. Where is it located? Oh snap, just left of 0. That looks like negative 2. Wait, that's a positive axis. That's 2, 0. And right, the point 2, 0 is a minimum. Yeah. Okay, then what? Do we have a saddle in there? Well, yeah, we do. The saddle point is right here. Does everybody see it? Is everyone looking? Everyone looking? Okay, so yeah, there's your saddle point. You can see it right there. That's where you'd step into the pants. And then you can see it right there. Okay, so there's our saddle. And where's that point? Oh, it's right on the other side at negative 2, 0. So look at those 2 points. We're looking down on it. We're looking down from above, and you can see them both right. You can see that both right there. There's the minimum point. There's the saddle point. One is to the left 2. One is right 2. And sure enough, one's a min and one's a saddle. If you don't think that this is really cool what you just did, there's nothing else for me to say. Because you already see me up here panting. I'm out of breath with how cool this is. Okay. Well, my phone went off a while ago. We should take a break. And then, oh yeah, there's still a little bit to go here. So we'll come back to one word problem, and then we will do our last section called Lagrange multipliers. So the time is 3:25. Let's say I'll be back at 3:35. Everybody go. You're all still sitting. You must be as exhausted with excitement as I am. Not even able to leave your seat. I'm gonna go home today and be like friends, family. I can find extrema and saddle points of multivariable functions. What did you do today?
And you get yelled at for saying something.
You would? Well,
I worked all day.
you got me there. Your job?
Yes.
And when
Huh? You should still just.
I know, that's what it is.
It is. What's the worst thing you have to do is not pay. That's
You
not-
do
that's-
something I want to do.
It's not good.
Yeah, 'cause if I'm going for that job and I don't get it.
Then you just don't have something better. So. That's all I need.
Yeah, now you're like,
When did you post all the solutions?
Oh, just before class.
That's what I thought. Like I've been.
Oh, I'm sorry, Simone. Yeah, I finished them all last night.
Like, you know,
Well, where's is that the original? Okay, so if this is the original, you can't write down x, y yet, because that makes me think that already is the answer to x, y. Okay, so if you want to find x, y, the first thing you're going to do is find x. And then the next thing you do is you do y. Okay, so you go in order from left to right. First you do the x, then you do with respect to y. So here's your equation. First, let's do it with respect to x. First, with respect to x, it'll be 3x squared. What? Is that 12x? Or is that a plus? Minus 12x, so minus 12, and the y squared goes away. Okay, now we do it with respect to y. But that's a constant, and that's a constant, so it's nothing. Where did you get that from? No, but which one was it?
Oh, just 2y.
Oh, here it is, x cubed, but minus 12x plus y squared. Yeah. So if you want x, y, and yeah, that's what I got as well. The answer is 0.
Yeah, the answer is 0, but I don't know how.
Oh, how? Because, okay, so that's what we just did. First, we take the derivative with respect to x.
Yes.
So that's definitely 3x squared, that's definitely minus 12, and then there is no x variable there, so it's just a constant, so that's 0. Now, take the derivative of both of those with respect to y. And since there's no y variable there, this is just a constant, and the derivative of a constant is nothing. And that's just a number, that's a constant, so the derivative of a constant is nothing. So f little xy is 0. Does that make sense? Okay, bye.
Obviously.
Damn, welcome on the morning.
No, listen, I can't.
That's what it is. You do,
That's really how it be. Mr. B, can we stay in this class for office hours or we have to go to your office?
Simone, because you asked,
We have to go.
we can stay in this or stay right here.
Ah, great.
Which means everybody could just do office hours. I mean, I've already had class with all of you guys, so yeah, we might as well just look at everybody's graph or paper. And
Okay.
but you're gonna stay and ask questions, right?
Yeah, I do have questions.
Great. Yeah, we'll just do office hours here, Simone. How's that?
Thank you.
Simone, you're not gonna believe this, but I was gonna say that anyway.
Oh.
But I'm glad you asked.
You only did it because I was feeling. Oh, let me tell you about the last week. So I was trying to. I'm not to cry. Oh my god. Pick it up. There. I know.
They're just bad.
I could have bought a spray and put it back on. Oh my god.
It looks so funny.
Yeah. I took that class. I'm like, I don't get it. I'm like, I don't know how I got it.
Were you just doing like in the command line?
When I was literally, I only had 2 commands. Well, okay, so I learned it, forgot it. Got to the job, and I got to use it.
Still have
You use Linux?
Mhm.
why?
Just got a different commands. Only
Scared?
No. And I heard like something like that. I don't know what her is. It's like they'll if you don't have it, then it's no. My brother and sister have it.
Oh.
But my brother didn't ever tell me to try it.
Mhm.
My cousin, I think
My
I'm
job
taught.
was like,
I'm like, dude, you're like, I have a child.
to sneeze
That's fun.
and get
I don't know.
See? I don't just do it. Because they have.
Who?
My mom makes fun of you.
Yeah.
I was like, what? Like, I didn't want to know that. Like, me too. Like, over winter break.
All right, folks, let's do it. We're about to have a lot of fun.
My dad.
What we're going to do is one last word problem, and then we're going to do our last section, section 7.4. Everybody ready? called Lagrange multipliers. So let's finish our word problem. The problem we're about to do, first of all, is very similar to what you'll see on the test. So write down everything. And it's just a word problem application of what we have been doing. So consider, suppose that labor cost for a building is approximated by this, where X is the number of days of skilled labor that you need to hire, and Y is the number of days of semi-skilled labor that you need to hire. So imagine you're constructing a building, and you need to hire some people who are skilled, like maybe they run the saw, or they do the plumbing or the electrical, and then other people who you don't need to have skilled in anything because they're just going to be running different rates. What?
I just made.
Okay. You want to share with everybody?
No.
Okay, that's fine. All right, so your total cost then is a function of both the skilled labor you're hiring and the non-skilled labor that you're hiring. And that's your cost function. So remember, what can you do with this information? First of all, you can calculate your total cost by just plugging in how many skilled laborers you have and any unskilled laborers you have. Boom, now you know your total cost. But you could also calculate the derivative with respect to X, and that would tell you the cost of one additional skilled laborer. Or if you calculate the derivative with respect to Y, that would be the cost of one additional unskilled laborer, right? So however many people you already have, C sub little x will tell you the cost of one more skilled, and C sub little y will tell you the cost of one more unskilled. Okay, but what do we actually want to do? It says find the value of x and y that minimize cost. Okay, so we have this cost function, and since it's going to be a minimum, they're already telling us it's a minimum, we can already kind of imagine that it's going to look something like this, right? That our cost function is some sort of a minimum. And so what are we really looking for? We're just looking for the flat spot. Right, so how do we find the flat spot? So how do we find the flat spot?
Find the derivative.
Well, yeah, you can graph it. But yeah, we're going to find the first derivative, second derivative, set them both equal to 0, and solve for our flat spot in space. And then we'll calculate the discriminant just to make sure that it really is a minimum. Because it could be that there is no minimum cost. You know, that's all they're suggesting they want to do, but we have to check. So the cost with respect to x, so first derivative with respect to x, so derivative of 10x squared is 20x, derivative of 5y squared is nothing, derivative of negative 240x is negative 240, derivative of 360y is nothing, derivative of 18,000 is nothing. So there's our first derivative with respect to x. Isn't that a nice first derivative? What's so great about it?
You could just solve it.
Yeah, there's no y, you can just solve it. So now we know the x location of our flat spot, 20x equals 240, is x equals 12. And what does that mean again? Remember that x is skilled labor and y is unskilled labor. So far our critical point consists of 12 skilled laborers. So now we take the first derivative with respect to y. So the first derivative with respect to y, going back to the beginning, derivative of 10x squared is nothing, derivative of 5y squared is 10y. Derivative of 240x is nothing, derivative of negative 360y is minus 360. And derivative of 18,000 is nothing. So now we say that equals 0. And solve. And y equals 360, so y equals 36. And what is that? Unskilled labor. Oh, so this one is skilled labor. So what we just found out is that the moment at which you have 12 skilled laborers and 36 unskilled laborers, it is a flat spot on the cost graph. But we don't know yet if it's a max, a min, or a saddle. So now we proceed. Now that we've done all of our first derivatives, what do? We've done all of our first derivatives. Now we do our second derivatives. So now we're going to do c little x little x. So with respect to x, the derivative of 20x is just 20. And now we need to find c little y. So taking the derivative with respect to y, it's just 10. And now we need to take c little x little y, which means take your derivative with respect to x, which we have already, and now take the derivative of that with respect to y. And Todd, I'm going to ask you for that. What's the derivative of c little x now with respect to y? Take the derivative of this with respect to y.
0.
Yeah, 0 is the answer. Yeah, since there's no y variable, it's just a constant.
Zero.
Yeah, so 0, the whole thing is 0. So Bata, this is like that problem that we were talking about earlier. Okay, so there's all of my partial second derivatives. You'll notice none of them have any variables in them. So when we go to calculate d, we don't even have to plug in our flat spot. So d is equal to, not f, c. I mean, the formula is f, but we're going to write down c. So c little x at the coordinate 1236 times c little y at the coordinate 1236 minus c little x little y at the coordinate 1236 squared. So note that that is your discriminant formula. By the way, it's fairly easy to remember the discriminant formula because it's going to be xx, yy, and then xy squared. Okay, and since these formulas are so simple, there's no variables for you to plug anything in, we're just substituting minus 0 squared. And so d is equal to 200. And therefore, is d positive, negative, or 0?
Positive.
D is positive. And remember, if d is positive, that means it's either a max or a min. And what's our second derivative with respect to x? Also positive. So if your second derivative is positive, remember that means concave up, and therefore you're talking about a minimum. So is it a minimum just like they said? They said they wanted us to minimize cost. And indeed, that coordinate is a minimum. And so we now know that we want x to be 12 and y to be 36. Now the question was find the x and y that minimize cost. But the real thing you want to find now is the minimum cost. So now you would go ahead and plug in c of 1236. Notice that's c of 1236, actual cost, not the derivative, not the first derivative, not the second derivative. We're actually curious to know what is the minimum cost. And notice now what an elaborate answer you can give. You can say, first of all, I do know how many people you should hire, first of all, 12 skilled and 36 unskilled. And I'll tell you how much that's going to cost you, which is the smallest amount of cost you'll have to pay. So let's see, it's 10x squared plus 5y squared minus 240x minus 360y plus 18,000. I don't know about the rest of you, but I got $10,000 and $10,080. So there we go. That's the least amount of cost it's going to cost you to build that building. Which I'm pretty sure if I could build a building for $10,000, I'd go do it. $10,000 doesn't sound like a lot to build a building. Yeah, I mean, what is that, a doghouse? Maybe a shed in your backyard? Yeah, a very, very small one-bedroom apartment or a studio, maybe. Okay, well, there we go, folks. That's a nice application of discriminant. The discriminant is what we were just testing right there. Because, you know, first derivatives is slope, second derivatives is concavity, and then discriminant is telling you, is that flat spot a max, a min, or a saddle? Everyone, you can all cross out 22. I did 22 on the answer key, so if you want to, you can go home online and you can look at it, but we're not going to do it right now. Okay, we're on to our last skill, and it's called Lagrange multipliers. Now, first of all, I cannot help myself. Every time I see the word Lagrange, I don't want to say Lagrange. I say, because it's French, I say Lagrange. Don't you just want to say it? Lagrange. So Lagrange, he was a mathematician in France in the 1700s. Bit of a brilliant genius. You know, we don't ever hear about him. You know, people talk about Einstein and Stephen Hawking and Newton, but Lagrange doesn't get much press.
And Mr. G.
And Mr. G, right, right. So Lagrange was a very skillful mathematician.
And he came up with this procedure that we're about to see. Now, I have to admit, the procedure that we're about to write down may seem arbitrary at first. So let's begin by just understanding what the question says, okay? It says we want to find the minimum of f of xy equals x squared plus y squared, subject to this requirement that the x-coordinate plus the y-coordinate has to be equal to 1. So notice that this is a very different type of question. They're not just saying to minimize that. If they were just saying to minimize that, you would just look at it and find the smallest point. So I could just go ahead and go over here and graph it, and it'd be x squared plus y squared. And my graph would be a parabola, all right? So if I just said minimize the function, that would be obvious. The minimum is way out there. In fact, where is the minimum? What's the coordinate on the xy axis on the graph? 0, 0. Right? So that's the minimum value of the function. But see, that's not what Lagrange is asking. He's asking what's the minimum value on this whole shape, such that the x-coordinate plus the y-coordinate is equal to 1. Okay, that's very different. So what's the smallest value of the function where x and y add up to 1? So let's just look at this for a minute. I want the smallest value of x squared plus y squared, but I also want x plus y to add up to 1. So first of all, let's just make a table of values here. What are some possible values of x and y to add up to 1? It could be 0.75 and 0.25. It could be 0.5 and 0.5. It could be 0.25 and 0.75. It could be 0.1 and 0.9. Or it could be 1 and 0. So does everyone agree that I just threw up a whole big smattering of coordinates that all add up to 1? So now the question is, which one of these produces the smallest value of this? So now what I'm going to do is I'm going to take those coordinates and compute x squared plus y squared. So you don't all have to do this yourself, but I'm going to type these in, square them, and add them together. So the first one is 1. I was able to do that one in my head. 0 squared plus 1 squared is 1. Okay, so 0.75 squared plus 0.25 squared, that's 0.625. 0.5 squared plus 0.5 squared is 0.5. 0.25 squared plus 0.75 squared is going to be the same value, 0.625. 0.1 squared plus 0.9 squared? I know you're all on the edge of your seat. 0.82. And 1 squared, that's 1. Okay, so you'll notice that depending on what I choose for x and y, provided they always add up to 1, I get a lot of different values for x squared plus y squared. Which one of them minimizes? Okay, it says find the minimum value. So where's the minimum value? What's the smallest value you see here?
625.
No? 0.5. 0.5. And therefore, it appears, that would be a nice solution because it appears as though the best choice is just to make x and y both half of 1. So at least, by crunching some numbers on a calculator, do we have the answer? What's the minimum value of x squared plus y squared provided that x and y have to add up to 1? We already know the answer. Everybody write down the answer. X equals 0.5, y equals 0.5. Now you might now say, come on, Lagrange, that was easy. Mr. G did it with a table of values. What's the big deal? Why do you get to name this after you all day? Lagrange multiply. Well, because sometimes it's not that obvious, right? This particular function that we had was symmetric in x and y. X and y were both the same thing. It's x squared and y squared. So that makes sense that the values were symmetric. But look at this next one. It's x squared plus 2y squared minus xy. Ooh. And this time we want x and y to add up to 8. Okay, there's no guarantee that it would just be 4 and 4 because y squared is weighted more heavily, first of all. So who knows? Maybe you'd want to have 1 and 7. Or maybe you'd want 7 and 1. I mean, who knows what possible combination is. And if you did this by hand, you'd have to sit there and just plug a whole bunch of values of x plus y into like an Excel spreadsheet, and then calculate this for every pair of numbers and see which one gives you the smallest. You could do that with Excel, but Lagrange didn't have Excel in the 1700s. So what we're about to see is a method Lagrange came up with using calculus that allows you to do this procedure without technology. All right? So is everyone clear on what we're trying to do? We're not trying to find the minimum of that function. We're trying to find the minimum of that function given the requirement that the coordinates have to add up to 1. And like here, we don't just want to find the overall minimum of this shape. We want to find the smallest value when the coordinates add up to 8. All right, this is a very different type of thing. Okay, so all that said now, the first thing we want to know is that we want to turn this requirement, bring it over here. We're going to call that the requirement. That's our requirement. And we want to move all terms left. So that's going to be x plus y minus 1 equals 0. Everyone see what I did? I just moved the 1 over to the left. And then we're going to call this expression g of xy. X plus y minus 1. That g of xy is a multivariable function in and of itself, and it is what we will call the requirement. Not the room of requirement, if you watch Harry Potter, just the function of requirement. We require, this is what we're requiring, that the x and the y coordinate add up to 1. Okay, so now, next, we're going to write down the Lagrange function. Let's define it. The Lagrange function is actually a 3-variable function. We call it f of the variables x, y, and the Greek letter lambda. The Greek letter lambda. Folks, lambda is a tough one to make. You basically do a curvy and then a backslash. Curvy, backslash, curvy, backslash, curvy, backslash. The first time you will have been using the letter lambda. It's a little awkward to draw at first, but that's what it looks like. Okay, so we're going to create a 3-variable function, which is this. First of all, the function that we want to find the minimum of minus lambda times g of xy. That's just what is called the Lagrange function. Now, if all of a sudden right now in the back of your brain you're like, what? That's a fine response. Where did that come from? Well, remember, Lagrange was a genius. He was somehow able to figure out that this thing actually meant something, that it could be useful, that this thing that we just did here, by taking the function that you want to minimize and taking the requirement that you want and multiplying in this dummy variable lambda, that we're about to do something and find the actual minimum that we're looking for. Okay, so everybody's ready with the Lagrange function? Now let's actually find it. So the Lagrange function, f of x comma y comma lambda, is x squared plus y squared minus lambda times x plus y minus 1. So in this particular case, this is the Lagrange function that we're looking at. Let's distribute the lambda and actually get this solved. So f of x comma y comma lambda is x squared plus y squared minus lambda x minus lambda y plus lambda. Yep. Again, I'm going to remove number 24 from visual view so it doesn't mess with us, but we're not canceling that problem. We're still going to do it. I just didn't give myself enough room. I didn't give anybody enough room. You might run out of space. I was able to do these problems in the space that you had, but I wrote tiny and I knew where I was going. Okay, so now, everything we've done so, what? Yeah. So everything we've done so far is just setting up the problem, okay? We took our requirement and turned it into a function. We have the definition of the Lagrange function. We've plugged everything in and we've distributed. So now here's what we're going to do. We're going to find the derivative with respect to x. We're going to find the derivative with respect to y. And we're going to find the derivative with respect to lambda. And we're going to set all of those equal to 0. So let's do it. What's the derivative with respect to x?
The derivative of x squared is 2x.
2x minus lambda.
Yeah, it's just 2x minus lambda. Because everything else goes away. Because y is a constant, lambda is a constant. We're only treating x as a variable. So all those other terms go away. It's just the derivative of x squared is 2x. Derivative of y squared goes away. Derivative of negative lambda x is just negative lambda. Because we're treating lambda like a constant. And then derivative of lambda y goes away, derivative of lambda goes away. So there's that. Okay, so how about the derivative with respect to y?
2y minus lambda.
Yeah, 2y minus lambda. Now the derivative with respect to lambda, and keep in mind lambda is kind of like it's our own variable. It is a variable. It's part of our multivariable function. Now we're taking the derivative with respect to lambda. That means x squared is just a constant. It's gone. Y squared is a constant. It's gone. Now with respect to lambda, lambda is the variable. So the derivative of negative lambda x would be negative x. So now we have negative x, negative y, plus 1. And what you'll notice, and this is true every single time you take the derivative with respect to lambda, you get back the original requirement function, but all the signs have changed. I mean, that's something you could just memorize. Whenever you take the partial derivative with respect to lambda, you get the original requirement formula back, but it's opposite signs. Okay, so now what do? We set each of these equal to 0. And we're going to solve for x and y. Because remember, what are we trying to do? We're trying to solve for the value of x and y that adds up to 0 and has the smallest possible value. So now what we're going to do is we're going to take these 3 formulas we got, so this one, and this one, and this one, and we're going to solve for x, y. Because remember, that's what we're looking for, is a coordinate in space. It's not a flat spot that we're looking for. It's just the coordinate that provides the smallest value of x squared plus y squared. We're not solving for a flat spot per se. It's just the coordinate that provides the smallest value of the function. Okay, so here's what you're going to do every single time, folks. You'll notice that 2 of your equations have lambda in it, and the third one, by definition, does not have lambda in it. Since we just took the derivative with respect to lambda, all the lambdas went away. Okay, so the first thing we're going to do is we're going to take the top 2 equations that do have lambda in it, and our goal is to cancel out lambda. Because that will give us just a simple equation with the third equation, x and y. So let's cancel out lambda. Let's do it. If I go ahead and write down, notice we're going to do this the easiest way possible. If I stack these equations on top of each other, 2x minus lambda equals 0, and 2y minus lambda equals 0. What's the easiest way to cancel, i.e. eliminate lambda?
Make one of them positive.
Yeah, just make one of them positive, right? So I'm going to multiply the entire top equation by -1. And what is the effect of multiplying an entire equation by -1? It doesn't turn everything negative.
Change the sign.
It changes all the signs, right? So there we go. I just changed the signs on the top equation. I add them together. The lambdas cancel out. And now I have 2y minus 2x equals 0. That's one equation. And now I also have this other equation. Now remember, the other equation is simply the original requirement equation, where all the signs were changed, right? But notice this equation now is the original requirement equation. We want x plus y. So look, if I just move the x to the other side and the y to the other side, what do I get? X plus y equals 1. That was the original requirement equation. So really, once you cancel out your lambdas, you're going to solve this equation with the original requirement equation, which is x plus y equals 1. So there's our system. And it's like we're all the way back to the beginning of chapter 2. Just talked about solving systems. You can solve it with substitution, elimination, inverses, discriminants, graphing, whatever you want to do. But obviously the easiest method would be elimination. Oh, I wrote the x and the y in the wrong order. Shouldn't I put them in the same order as the ones above?
Yeah.
Yeah. So really I have y plus x. And now I want to eliminate, what? Should I eliminate x? Because already 1 is positive and 1 is negative.
Yeah.
So I'll multiply the bottom one by 2. That gives me 2y plus 2x equals 2.
I still have my first equation, which was 2y minus 2x equals 0. Now I can add them together. The x's cancel out. 4y equals 2. And now I divide off the 4, and I get y equals 1/2. OMG. Y is 1/2? Was it 1/2? It was 1/2. And furthermore, now we need to solve for x. Well, we have a requirement equation. If the requirement states that x plus y had better add up to 1, and I now know that y is equal to 1/2, what must x be? 1/2 as well. So we now know that x is 1/2 and y is 1/2. Now, what is that coordinate? Okay, we just found a coordinate. That coordinate is what? Is it a flat spot? No. Remember, we're no longer trying to find the global minimum. If I wanted the global minimum, the bottom of this shape is at 0, 0. What I wanted was a coordinate in space where the x plus y adds up to 1 that gives the smallest value of this function. And the smallest value will be at 1/2, 1/2, which will be just off, just a little bit off from the bottom. Right? So not at the very bottom, but just a little bit up at the coordinate 1/2, 1/2. Yeah. We did it. So that whole thing was called Lagrange multiplier. Now, folks, can I just share something with you? Before you get too excited or worried, this formula, D equals F little XX AB plus F little YY. No, not plus, times. Times F little YY AB minus F little XY AB squared. I'm going to give that to you on the test. So you don't have to worry about memorizing it, okay? And now this whole Lagrange formula, which is F little xy minus lambda times G little xy. I'll give that to you on the test too. Okay, so you don't have to worry about memorizing these formulas. You just need to know how to apply them. Okay, does that take off some stress? No?
You just give me a take.
Nope. Okay, just for asking, now you have a B. Okay, everybody ready to try the next one? No. Oh, good. Everybody's on board. So the next question I crossed out so we wouldn't see it. Now let's again, before we try solving the problem, think about what it's saying. So here's number 24, and we're looking at the function f of xy, which is x squared plus 2y squared minus xy.
Is there an easier way to do all this?
No. Okay. Now, subject to the requirement that x plus y equals 8. So the requirement is that x plus y equals 8. So again, let's think about what that means. If I were to make a table of values, and I have all my x values, all my y values, that add up to 8. So it could be that I have 0 and 8, or 1 and 7, or 2 and 6, or 3 and 5, or 4 and 4, and so on. And then I would take each of those pairs of numbers. But keep in mind, it's not just whole numbers that we're interested in, right? It could be halvesies. It could be decimals.
Nice.
It could be 0.1 and 7.9, 0.2 and 7.8. Like, imagine how many you'd have to check. You'd have to check a lot. But if you did go through and you made an Excel spreadsheet, so Adon, you were wondering, is there another way to do this? You could do an Excel spreadsheet. But how far do you have to take the decimals? What you'd really have to do is 0.01, 7.99, 0.02, 7.98, and then you're at least, really sifting through. But even then, the real answer could be 0.0004 and 7.9996. Who's to know? So doing it on an Excel spreadsheet could get you close, but not the true answer. Okay, so we're wondering, we want a coordinate where the x and y adds up to 8, and I want this thing to be a what? The smallest it can be. Now everybody just look. I want to make this thing as small as possible. And x squared is just x squared, but y squared is times 2. So does everyone agree that a good idea would be to make the y variable as small as possible? Or at the very least, smaller than x. Because what the y is being squared and multiplied by 2. So I would definitely want my x value to be bigger than my y value. And that's already something I know for sure. I'm probably looking somewhere in these values right here, where the x is bigger than y. Because I want to make y as small as possible. Yeah, you could even guess, why not just guess, make y equals 0? You know, does anyone think that that would be a good guess? Just make y equal to nothing, and then make x equal to 8. And maybe that's the smallest possible value for all we know. But maybe not, because I also want to take advantage of this thing, which is subtracting. Right? I want to minimize this. And so here's a term for subtraction. I would love to subtract, because that would make the value even smaller. So maybe that means don't make y 0. Maybe make y some teeny little thing. So that way you do actually get to subtract something. Okay, so needless to say, we're erring towards the idea that our value is going to be an x value larger than a y value. It's somewhere in there. So everyone ready to do it? Here's our steps. First, the requirement. Remember, the requirement. Move all the terms to the left so that it's x plus y minus 8 equals 0. And that thing right there is the requirement formula. G of xy equals x plus y minus 8. We have to write down the requirement formula first. Next, we'd write down the Lagrange formula. I never get tired of it, folks. Never. So now the Lagrange function is f. And I tell you what, folks. We can be friends. We have to keep writing parentheses, x comma y comma lambda over and over and over. I won't tell if you won't tell. But if any of you tells, I'll deny it. I'll say, of course I kept writing comma x comma y comma lambda. What? I know I'm recording myself, but I'll deny it. So our Lagrange function is f of xy minus lambda times g of xy. Right? So the function we're trying to minimize, the requirement function times lambda. So let's go ahead and plug all that in. We've got x squared plus 2y squared minus xy minus lambda times x plus y minus 8. That's just writing in what the functions are. Now I'll simplify it. X squared plus 2y squared minus xy minus lambda x minus lambda y plus 8 lambda. Whoa. At which point you're like, thanks, Lagrange. So there's our Lagrange function. See, Lagrange. How great would that to name your child Lagrange?
Hey, Lagrange, come here.
Exactly. I'm so telling my wife about this. I want to name our next son Lagrange. I also wanted to name our son, because we just had a son a couple months ago. I wanted to name him D'Artagnan. Wouldn't that be great? D'Artagnan. I mean, what names have an apostrophe in it? Simone. Right? Simone is lucky. She has an apostrophe in her name. If I can't have D'Artagnan, I'm getting Lagrange.
What is your son's name?
Augustus. Oh, that's bad. All right, well, thank you, folks. Okay, so now let's keep going. We're done. We have our Lagrange functions. Now we take our derivatives. Derivatives. You know what my consolation prize? As soon as we had our second child, we had to get a minivan because that's what happens when you have kids. I got to name the minivan D'Artagnan. So the minivan's official name is D'Artagnan. That's my 2.5-year-old daughter. She'll tell you. Minivan's name is D'Artagnan. Okay, derivatives. So we want f little x. And again, we don't have to write all that parenthesis business. Just take the first derivative with respect to x. So what is that then? 2x. The 2y squared goes away. The derivative with respect to x of negative, that would just be negative y, right?
Yeah.
And then minus lambda. Because the derivative with respect to x, we would keep the lambda, and the rest of those go away. So there's our first equation that we get to use later on in solving our system. Now, the derivative with respect to y. So x squared goes away, 2y squared becomes 4y. Derivative of negative xy with respect to y just becomes negative x. And the derivative with respect to y is just going to be negative lambda. And the rest of the terms go away.
I just kind of glossed over that real quick. I hope you're all feeling comfortable with taking derivatives with respect to one particular variable and ignoring the other ones. If that still isn't clicking for you, make sure you see me after class so we can do some more examples. So now, f with respect to lambda, I already told you what the answer is going to be. The answer is just the requirement with all the signs changed. But again, if you take the derivative with respect to lambda, it's negative x minus y plus 8. Which, when you set that equal to 0, you can move the x and the y over, and you simply get the requirement formula. F sub lambda is always just going to be the requirement formula that you started with.
Switch sides.
Well, yeah, with the sign switched, but when you move the x and y to the other side, you literally get the requirement formula. Yeah. Okay, so now what do we do? Who remembers what we do? You take the first two, f little x, f little y, and what do?
Get rid of, cancel out the lambda.
Yeah, we want to cancel out the lambda. So I'm going to bring those all the way over to where I can deal with them. A little taller up on the board here. So I've got 2x minus y minus lambda is 0. And I've got 4y minus x. I'm going to change the order there. It's 4y minus x. That means it's negative 1x plus 4y. Why did I change the order? Yeah, I need to have everything stacked, right? You got to stack your x's on top of the x's, y's on top of the y's, lambdas on top of the lambdas. Okay, now how do we cancel out a lambda?
Just send one to be positive.
Yeah, well, we want to change all the signs of one equation, right? Because we want the lambdas to cancel out.
So we make the top -1.
So we can just multiply the entire top equation by -1, which means to change the positive 2x to a negative 2x, change the negative y to a positive y, change the negative lambda to a positive lambda. And now we can do elimination, cancel out those lambdas, and we get negative 3x plus 5y equals 0. That's one of our equations that we're going to solve as a system with the requirement equation. So now I'm going to go ahead and write down x plus y equals 8 right below it. And believe it or not, like all this work that we just did is all coming down to just solving that system. Because that system is going to tell us the coordinate that minimizes this function subject to the requirement that the two coordinates have to add up to 8. So it all comes down to this. And again, what's the easiest way to solve this system? Using a matrix, a determinant, inverse.
Matrix.
Well, or you could do the inverse matrix if you like, but I think elimination is the easiest, right? Like that's a negative 3x, what do I want this to be? Positive 3x. Like after everything is said at the end of the day, elimination is such a good method. So I multiply that one times 3. Now I have my negative 3x plus 5y equals 0. I add those two together. The x's cancel out. 8y equals 24. Y equals 3. And remember, x plus y has to add up to 8. X equals 5. So since they have to add up to 8, x must be 5. It's 5 and 3 add up to 8. Notice that was not where I was heading with my logic. I was thinking, hey, definitely x has to be bigger than y. But I was wondering if maybe it would be best to go all the way to this extreme to make y as small as possible. And in fact, no, the answer was to make y a little smaller than 4, 4. Like 4, 4 would be if you gave equal weight to x and y. But the actual solution was just to make y a little smaller. And so now, what can we say? You'd say f of xy has a minimum value when the coordinate is 5, 3. Okay, that's not really good English. F of xy has a minimum 5, 3. And again, remember, not a global minimum value. That's not a global minimum value. That's not like the bottom of the actual shape. That's just the smallest value f of xy takes on, subject to the requirement that x plus y equals 8. So subject to the requirement that x plus y equals 8. So there are values of x and y you can plug into that function that will make the function even smaller. But those solutions wouldn't satisfy x plus y equals 8.
Okay, how's everybody feeling? We just did 2 examples of the tangent function. No, the Lagrange function. Okay, I wrote down some notes to myself. We did those. Very good, I wanted to do those. We could do 25. Yeah, 25.
Skip 25.
Well, no, I mean, it all depends on how everyone's feeling. Okay, so basically it's 4:17. We get out of here at 4:45? No, I think it's 4:45. You can't mess with me. It's an alarm on my phone. So I say.
So you cut out the last 2 and start on the review.
Well, I do want to give us some time to do the review. All I had done was crossed out 26, but I still had left number 25. I do think it's important that you all try one on your own. Yeah, leave 25 as homework. I tell you what, you have to do 25. Do you want me to do it with you right now, or just leave it to you to do on your own?
Right now, because I'm like,
Most ways, honesty. Anyone else? We can do it real fast, just to see it. Do you guys want to see it?
Yeah.
Okay, let's do it. Because after all, we will still have a little time to review, and you have all the solutions to the practice test, and you have all weekend to study, and you have all Monday to study, and you can call me. So let's go ahead and do number 25. We want, now first of all, folks, we can already solve this problem, if you believe that. Because look at this function, 4xy. It's symmetric in the x and y variable. Neither variable holds more power than the other. Like if I had written up the function f of xy is x plus 40y, and we want to make this function as small as possible, what should you do to y? Make it tiny, right? Because it carries so much weight. You wouldn't want to put any weight in the y variable. You'd put most of the weight in the x variable. But this equation is perfectly symmetric in x and y. So, and you want 2 numbers that add up to 8. What would be your guess? 4. Our guess would probably be 4 and 4. That is the answer. I just checked my answer key. That is the answer. So, see, this is some really interesting high-level thinking stuff. The formula, if it's symmetric in the variable x and y, you can already guess. Just put an equal amount in the x and an equal amount in the y. Whereas if the formula is not symmetric, like this, does this make sense to everyone, what I'm saying about symmetric in both variables? Like, it matters which one you give more to. So since this is a symmetric equation, we already know the answer is x equals 4, y equals 4. Now that's super cheating, right? We didn't do the Lagrange function. But we know that that's what the answer is going to be. So now that we already know what the answer is going to be,
If we see that on a test, can we just write the answer, or do we need to do like all?
That won't be on the test, and you have to show all your work.
Okay.
Yeah. Okay, so let's do it. What was the first thing we have to do? Write down the requirement function. It's x plus y equals 8. We already know what the requirement function is. It's g of x comma y equals x plus y minus 8. Right? Because you just move the 8 over to the left, and that's your requirement function. Okay, so what is our Lagrange function? We know that it's f of x comma y minus lambda times g of x comma y. And therefore, f is 4xy minus lambda times x plus y minus 8. Third time's a charm, right? I hope that this third time of writing this down, you're feeling the flow. So I distribute my lambda. F is 4xy minus lambda x minus lambda y plus 8 lambda. And that's the Lagrange function, and now we start taking derivatives. So what's the derivative with respect to x? Yeah, that means you hold y constant. The derivative of 4x is 4. Y comes along to the right, so that's 4y. Very good. And then, with respect to x, just minus lambda, and the other 2 terms go away. So that's the derivative with respect to x. What about the derivative with respect to y? Now, the x is a constant, so the derivative of 4y is 4, so that's 4x. And then with respect to y, that goes away. This becomes negative lambda, and the other term goes away. So remember, these are our 2 equations, 2 of the equations. And the goal there is to take those 2 equations and cancel out the lambda. Right? So these 2 go together. I'm going to box them. So respect to lambda, I can appreciate how someone would say, gosh, there's no real work you have to do. It's immediately going to be negative x minus y plus 8, which if I set that equal to 0 and move all the terms, well, move the x and y to the other side, I just get my requirement. All right, so we know that f, the derivative of f with respect to lambda is simply the requirement function. Okay, so we write these two equations next to each other. How do I get lambda to cancel out? Yeah, multiply one of the equations by -1 to change the sign, so I'm going to change this one. Add those two together, the lambdas cancel out, and we get 4x minus 4y equals 0. And our other requirement was x plus y equals 8. I want you all to notice, and I hope you appreciate, that despite Lagrange's fancy name and the strangeness of the lambda times the requirement function, and taking partial first derivatives of a multivariable function, it all boils down to one of the easiest systems you've ever seen. Right? There's nothing really hard about this problem other than understanding what the process is and what the steps are. So now, which variable do you want to cancel out first? Yeah, why not cancel y? We already have a negative 4y, so let's make this a positive 4y. And then we'll have 4x minus 4y equals 0. 4x plus 4y equals 32. The y's cancel out, and I have 8x equals 32. And then x equals 4, which is what we originally guessed. Because it's symmetric in x and y, you'd give equal amounts to x and y, and the answer would be 4 and 4. Which we just concluded ourselves. Since x is 4, and then add to 8, we know y is also 4. Josue, are you happy we did it? All right. Now, was that problem hard? No, it's not hard. It's just the steps, right? You got some steps. Okay, well, dandy. We did end up with a little bit of time on our hands.
So are we gonna push the test device?
Oh, no.
Dad,
No, why on earth would we do that? Definitely not. You silly. You silly, Simone. Okay, there we go. There's our practice test. I got to write it there on the board. Now, folks, considering I gave you the solutions, how can we strategically use your time right now?
Go through problems we all don't know as a class.
Yeah, wonderful. Do you all have your practice test on you? Yeah. Okay, everybody come up here and vote on which problems you want to see. So, how many problems are on the test? Looks like
23.
25. 25 questions are on the test. So flip through right now, choose 3 problems you'd like to see, and then come up here and vote with a check mark about which one you'd actually like to see done. So 1, 2, 3.
There's 23.
Oh, 23?
Yeah.
Oh, okay, well,
You're
23 then.
being generous and took 2 off.
Good.
Unless there's 2 bonus questions.
Okay, well, while everyone comes up here to vote, the markers are on the ground because there's no shelf. Flip through, see which ones you want to see. If you want to vote 4 times, that's fine. You know, you can vote 4, check what. Yeah, that's the best I can do. So you can vote on more than 3 problems if you like, but just don't vote on all of them. Even if you did, it would just wash your result out because it's a good check mark next to every problem. I'm looking for which problems have the most check marks, and we'll do those problems together. And when you do that, I'll make sure I put the right practice test on the board.
Would you put y minus y sub 0 and
I think I expect you to know point slope form. I'm giving you discriminant and Lagrange.
Everything else right on our thigh.
No, memorize it. But thanks for letting me know your method, Adon.
No problem.
It is. Thank you, Josue. 1? You put 3 check marks. Well, find the ones that you.
Choose out. Yeah.
Number one.
Would you say number one?
Oh, okay, that's what I did.
I know.
Oh, and Simone, I'm giving you the discriminant formula for solving systems, not the inverse formula. Well, I'm kind of giving you the inverse formula too. I didn't hear it. What'd you say, Josue?
She says she doesn't need it. She wants to practice.
Oh, okay. Well, that's great, Simone. Well, it'll be there just in case you want to look at it.
I think we all voted.
You think you all know what?
I think we all voted.
You think?
Everybody voted.
Right.
Oh, everybody voted. Okay. I'm fixing my PowerPoint because my numbers were wrong, so I would have been off.
So is there going to be 25?
I think I've made it only 20, to say the truth. Like, not every problem on the practice test makes it onto the test.
Does it make the cut?
Right. Because a nice way of doing a test is you make someone study for more problems than they actually have to do. That might sound twisted, but
Yeah,
it's. To who? Who's that?
The accounting.
Hmm.
She doesn't put any problems.
Really?
Yeah, they're always doing something.
Yeah.
Yeah. She's like, let's work on balance sheets today. They may or may not be on the test. And it's like, something like that. All right.
I'm so glad y'all telling me that now because I was really studying.
And then she'll get mad.
No, if you really want to study, just study what's on the book. That's like
Read the book and watch the videos.
Teach yourself. Basically,
Yeah.
right?
Teach yourself.
She is, but like her tests are terrible.
Yeah,
I
same.
don't think she's a good teacher. I asked her questions.
Sorry, I did not turn off the
You don't
camera.
remember that from last year? No, let me tell you what she did. She did all this morning. Like, so, I got my things. I was like, okay, we're calling the next questions, if I need help. And I emailed her, "Can you be in the office hours at 8 o'clock?" And then she texted in her office at 8 to 9:30. She texted me back at 10:30 and said, "No, I won't be there." No, of course she won't. Right. I was here.
I mean, she knows what she's doing.
Doesn't she do?
But
She
she
doesn't know how to
expects me
explain
to
it.
know what she knows.
And she's like, "Oh my gosh, that's the
She's not.
problem."
Oh.
She's not organized. She doesn't. She like knows what she's talking about. She doesn't know how to explain it. So everyone else understands.
Oh, what's happening? I listened to she explain it to me. I was like, "Oh, can you explain it differently?" She's like, "No." And I was like, well, can I, like, she's like, you can ask me again, but I'm going to say the exact same thing.
No, they need to dumb it down.
Yeah, you know,
She yells
but I
at us.
understand it the first time.
She yells at me if I ask her for help. She's like, you should remember everything.
All right, folks. Let's do it. Oh, good. We did have some voting. All right. What I'm going to do is go to the ones that were most heavily voted for first, with the most chicken scratches, and then we'll go back and do the ones with the least chicken scratches. So let's go straight on ahead to which one has the most?
Number 10.
Number 10. Looks like 10 was popular.
It was just, it was long.
You know, one of my favorite things to do is like pranks. Number 10. Oh,
Wait, are you guys all just kidding?
No, we're serious on number 10.
Oh, okay. Well, everyone look at number 10. We're just adding the matrices. So, right? So it says find a matrix that gives the increase or the decrease in sales by each salesman for each type of insurance from July to August. So let's consider here, we're going from July to August. So from July to August, what did the sales do?
It increased
It
3,000.
increased by 3,000. So you'd write plus 3,000. And then from hazard, from July to August, what did it do? Decreased by 1,000. And then from July, from 16,000 to 14,000, what did it do?
Decreased 2,000.
It decreased 2,000. And then the last one from 27,000 to 21,000.
Decreased 6,000.
Yeah. Okay, well. That's the answer. Yeah, that's the answer.
Oh, no. That's it?
Yeah, that's it. That's why I asked if you were joking, because
I know, I'm like,
you just write down what
I know
happened.
that's what we're supposed to do.
I really didn't read it. I just
Well,
looked
let's look again. It says find a matrix that gives the increase or decrease in sales by each salesman. So that matrix gives the increase or
At
a
the top, I
decrease.
forgot to read the bottom part.
Ah, okay.
We're just testing to see if you can.
Well, thank you for that. All right, number 10.
wait, if for 11, if we just multiplied it, you okay with us using the calculator?
Well, let's go and read it, even though oh no, 2 people did vote. Okay, let's look at it. So a company makes 3 chocolate candies. Matrix A is the amount of ingredients. Matrix B gives the cost of the ingredients. Multiply the matrices and interpret the result. So first of all, in what order can you multiply them? A is a 3 by 3. And B is a 3 by 2, right? Rows by columns. So that must be the order in which we're multiplying. Because remember, the middle 2 numbers have to match. And the result is the outer 2 numbers. So the result will be a 3 by 2. So how are we multiplying them? A times B. So then you just type it in your calculator.
And then whatever answer we gave, we just
write it down.
okay.
Now what's interesting though is interpreting the results. So now notice, in matrix A, the rows, okay, so let's look at what our answer is. What are the unit of the answers? This 3 was the row of matrix A, and the rows of matrix A are what?
The candies.
Yeah, the candies themselves. So this is the candies. And then the column of the answer is the column of B. The column of B is
Ingredients.
suppliers X and Y. So then what's the result going to be? It's going to be a matrix of 3 by 2, where you've got the candy, cherry, almond, raisin, from each supplier. In other words, from supplier X, you're going to be able to make this many candies. And from supplier Y, I'm going to be able to make this many candies. It's helpful to put in all the labels, honestly. So for matrix A, the row is the candy, and the column is the ingredients. And you'll notice for the matrix B, the row is the ingredients, and the column is the suppliers. So notice, folks, the middle 2 numbers, not only do the numbers match, not only are they both a 3, but they're both talking about ingredients, right? So that's really what's going on, is that the middle 2 numbers have to match exactly, right? They're talking about the same thing, because now you know how to label your final matrix. And that's really what I'm looking for. So when you do actually type that into your calculator, and you type that into your calculator, if you just write down some numbers, I'm only going to give you half credit. What I want to see is you properly label the rows and properly label the columns. Okay? Because after all, what does it say in the instructions? It says interpret the result. It doesn't just say multiply the matrices. It says interpret the result. So the result is this matrix tells you the number of candies made from each supplier. Does that make sense? I mean, as a business person or an accountant, the most important thing other than being able to do math is to communicate your results to your client. Telling your client what on earth that matrix means. And if your client says, I'm sorry, I don't understand, tell it to me in a different way. And then you say, I'm just going to tell you the same way I just said it. No, you're going to say it to them differently, aren't you? Okay, next. The next heavily voted question, they're all 2s now. So I'm going to go back to 3, 9, 12, and I'm going to do those next because they had 2 votes. And then I'll go back and I'll do all the 1-vote questions. How does that sound? Perfect. Is that fair? Okay, so let's go back now to number 3. All right, find the equation of the line. Oh boy. You folks are going to love seeing this answer because you're going to say, oh man, this is all so easy. And you know what? All math becomes easy once you know how to do it. So watch closely. Find the equation of the line through that coordinate. So everybody watch real close. I'm going to draw a graph. Draw a graph through the coordinate -1, 2, 3, 4, -2. I want it through that coordinate, and I want the slope to be 0. What does 0 slope look like? It's just a horizontal line, right? What's the equation of that line? You have to have memorized that the equation of a horizontal line is y equals the y-intercept. And you have to have memorized that the equation of a vertical line is x equals the x-intercept. So,
Just a minute, y equals.
y equals -2. Yeah, that's it, y equals -2. So this is largely a graphical result. This is a result of you drawing a picture and just looking at it, right? How about number 4? Nobody voted for number 4, but we might as well say it. Now we want
X equals 0.
the equation of a line through -4, -3, and I want undefined slope. And what's undefined slope? Horizontal is m equals 0. Vertical is m equals undefined. So what kind of line am I drawing?
Undefined.
Yeah, a vertical line. And therefore, the equation is x equals the x-intercept. What's the x-intercept?
-4.
Yeah,
X
-4.
equals-
X equals -4. Very good. Very good, folks. Hard. Well, you know what is hard is just remembering all the definitions. And you know, one thing I've been saying a lot lately is when you get to a word problem or any problem, you can take a lot of stress off your shoulders by not telling yourself that your job is to solve the problem. Your job is to write down as much as you can. Because if you can just start writing down as much as you can, usually if you write enough, do you know what happens? Well, you found the answer, right? Like if you just start drawing and just start thinking about it, you're like, oh, it's a horizontal line, you know? Whereas if you just think, oh, what's the answer, and you write nothing down, you'll probably just stare at the paper for a while. So your job is to write down as much as you can. And if you write down a lot, you're eventually going to get to the answer. Okay, next question is number 9.
So for the answer for that one, because you just want to draw a picture and
Well, the question was, write the equation of the line. And that's the equation of the line.
okay.
Pictures will help. But yeah, pictures will help. Thank you, Don. Did you have that written on your thigh? Pictures will help?
Yep.
Yeah. All right. So Linda invests $25,000 for the year. I'll just help you set it up, okay? Now, the key here is that you have to solve this problem using the Gauss-Jordan method, which is matrix manipulations. You can check your answer by using an inverse or a determinant, but you have to show me the work of manipulating your matrix. So let's begin. Yeah, but this might be the last one we do. Maybe we can get to 12. That was a double voted one. So she invests $25,000 in 1 year. Part 1 is invested 5%, then 6%, then 8%. The total income from all 3 is $1,600. The income from the 5% and 6% is the same as the income from the 8%. Here's the key thing. Find the amount invested at each rate. So what are they asking for? Because the question will tell you how to define your variables. Find the amount of money invested in each rate. So everybody, you begin the problem by saying, let X equal the money in the 5% account, let Y equal the money in the 6% account, and let Z equal the money in the 8% account. Does everyone agree that that responds to the question, find the amount invested at each rate? Okay, so now that we have our variables defined, which you cannot do anything until you define your variables, we go back to the beginning and we think about what we said. Linda invests $25,000 for 1 year. So what's our first equation? What does x plus y plus z add up to? $25,000. Because she has $25,000, she invests it all in one of those three accounts, so those three variables must add up to $25,000. Okay. The next equation, keep in mind, follows the pattern percent times dollars plus percent times dollars plus percent times dollars should all be adding up to the total amount of interest that you get. So what does that tell us then? So 5% of X dollars plus 6, oops, that's 0.05, isn't it? 5% of X dollars plus 6% of Y dollars plus 8% of Z dollars should add up to the total interest of $1,600. So that's our second equation, but nobody likes the decimals, so what do?
Change it, or multiply it all by 100.
You multiply it all by 100 so that you get rid of the decimals. Now we just have 5x plus 6y plus 8z equals 160000, which is 160,000. So there's our second equation. How many equations are we trying to build? 3. How do we know? Exactly, because there's 3 variables. You better have 3 equations, or else you cannot solve it. Okay, so what's our third variable, or our third equation? The income from the 5 and 6% investment is the same as the income from the 8% investment. So that means that the 5% income plus the 6% income together is equal to the 8% income. That's is the same as the income from the 8% income. Again, we don't like the decimals, so we multiply through by 100. We get 5x plus 6y equals 8z. But remember, in order to do a matrix problem, you need x, y, z equals a number. So what do we do with the 8z?
Bring it over.
They bring it over to the left. 5x plus 6y minus 8z is equal to 0. And there's our third equation. Now, folks, the reason this question will be on the test, not the same numbers, but this question, is because we just did a whole bunch of work and we didn't even start solving the problem yet. Right? This is a really good problem. This is a real good life problem. So now what do? We take those 3 equations and we write them down in a matrix. So now we would write down, our matrix, just the coefficients, 1, 1, 1, 0.5000. And then the next one is 5, 6, 8, 160,000. Commas are helpful. And then 5, 6, negative 8, 0. Now you can begin to solve the problem.
And from there we just start solving, like trying to get the 1s and the 0s.
Exactly right. From there you start solving to get all those 1s and 0s. So remember, before you even start anything, you should write down your goal. Your goal is, what should that matrix look like when you're done? 1, 0, 0, 0, 1, 0, 0, 0, 1, with numbers. And what are those numbers? Those numbers are the solution. When you're all done, and remember the order that we're going to go in. You start by putting a 1 there, and then you make those zeros, and then you make a 1 there, and you make that a 0, and you can make that a 0 too if you want to. And then you make this a 1, and you make those zeros. Yeah, that would be the order of your work. Cool. Should I do that? I mean, we're almost out of time. Should I do that or take a peek at number 12? Let's just peek at number 12 because 2 of you voted. I want to answer it. Oh, solve this by using an inverse?
Oh,
You can all do that.
Yeah.
So you just turn this into matrix A, and you turn this into matrix B, and then you just type it in your calculator. So A, you type in -2, -6, 2, -1. And then B, you would type in -2 and -5. And then in your calculator, you would just type A inverse times B. And that literally is going to tell you the solution. Right? So for those people who voted for 12, does that answer your question?
Yeah.
Okay. Okay, would anyone like to see us finish solving 9? Okay, well then let me just wrap up. Jeez. Wait, who was that, David? Everybody's a comedian. Okay. Yeah, okay, so what do we need to say? I'm gonna hold office hours right here, right now. So anybody who wants to stay for office hours, you can stay. All of you need to show, all of you need to come to office hours to fulfill my requirement, but you've all been in my class before. So how about just all of you have your notes out from today and just let me come look. I just wanna see how your notes are doing and that you're, writing everything down, and then you can all call it done. And then whoever wants to stay, you can stay. Just today's notes. Just today's notes. I just want to see how you did with the Lagrange.
Yeah, I know, right?
Oh my.
Ah, very good. Okay, very good. So
You're what?
you're done. Okay. Oh, yeah, very nice.
For yourself.
Oh, yeah. Oh, yeah. Okay. Bottom have to get up. And David, I'll take this for this. I take this for Diego.
I go straight to 16th
Ah,
Street,
super.
up to Bell, straight up.
No, that's what I said.
And hey, very nice. Yep, that looks good. Hey, Luis, very nice. Very nice. There we go. There we go. Luis. When you're a goody two-shoe?
Yeah. So,
Yeah, that's why I said Tuesdays.
Thursdays off. Okay, that looks better.
yeah,
That was
it's a
expected.
lot.
Now I work Monday, Wednesday.
Okay, so, okay, yeah.
Thank you.
I mean, seriously, come on, who has a name with an apostrophe?
I know,
It's unheard of.
it's so classy.
It is classy. Yeah, that's why I wanted to change. Who knows, maybe my wife will change her mind.
To change his name.
No, the next son could be named her name.
Oh, you want more? You want more?
Well, we either want 3 or 4, thank you.
Oh. At least that's a team.
Well, Simone, I'll tell you the story. See, when we got married, my wife wanted 4, and I wanted 2. So we compromised, and we're gonna have 4.
Damn. That's how that goes, huh?
Yep. But the funny thing is, after 2, she's like, okay, maybe 3 will be fine. Now that she's been there, done that. Because she had natural birth 4 times. She didn't take any drugs.
No.
And she refuses. She only wants to do it the natural way. So she's like, maybe just 1 more. Maybe 4 is a bit much.
It's a lot.
Okay, I don't know if anybody wants to
I feel so bad.
see this one.
I don't even have kids. That's painful.
Bata, you have any questions? You what?
I got a new calculator, so.
That's a great calculator, Bata. That's a good calculator. So do you need to know how to do the matrix? Okay, Bata will show you. So first, you see the word matrix? Okay, the second matrix, we'll turn it on first. The second matrix. Very good. Now, you're gonna go over to edit for the most part, and after enter, you're gonna edit matrix A. Well, that's just an arrow. These are arrows. You're moving your cursor.
Aw.
Okay, so you go over to edit, hit enter.
Because I don't have class at 6.
Now, so you're gonna edit a matrix. We might as
Yeah, I
well
have my
do
computer, so I'm like.
the one that I just
got
mentioned. This is practice test, right? Yeah.
I'm so
Let's do
depressed.
the inverse question.
I'm broke. I could be at home.
There we go.
watching
This one.
HBO.
So
we're gonna do a 2 by 2 matrix and then a 2 by 1 matrix. So change and hit 2, enter, 2, enter. You constantly hit enter, so 2, enter, 2, enter.
Good.
So you just said a
They
2
got
by 2 matrix.
internship.
Now, we always hold our calculator in our hand when we do this, so that you can type quickly and efficiently here. So you're gonna go, whoops, -2, enter, -6, enter, 2, enter,
No,
-1.
because you explained it.
You read
she
from left
never
to
told
right
me
now.
anything. She explained.
Okay, so now I'm gonna type in zeros.
The way she was.
Type in all the numbers.
I knew what she was talking about.
Yeah, just the ones on the left.
She's like, actually.
The 4 numbers with
I
the
was
X
like,
and
I
Y.
won't say that.
She's mad because she's not, she should have been told me your name. But she,
Bro.
Enter.
and then, but she only told me to first, and then I was like, I can't.
Good.
I
Okay, so
know.
now that's matrix A. Because notice
When
we
you
have
told me
A,
about
X,
rework, I was like, so it
So A
is.
is the
Yeah.
matrix, coefficients on X and Y. B is
I
just
was
that.
like, I won't say
little
nothing.
thing. So now hit second matrix again.
Second.
Good, go back to edit, and then go down.
I think that is.
Now we're gonna edit matrix B, so
No,
enter.
why minus.
Now we want this to be a 2 by 1 matrix, 2 rows,
Yeah.
1 column, so
Yeah.
2, enter, 1, enter. Good, and now you're gonna put in -2, negative. Good, now hit second quit. Okay, now this is where we're gonna do our actual computation. And what we're gonna do is A inverse times B. So there's the inverse button, X to the inverse, that's X to the -1. So and you'll notice that's the same button you hit to get to the matrix. So now hit second matrix.
Then it was 25.
Damn, they're trying to
So now we're
I
on the
know.
matrix.
That's
Now you
what
didn't
I'm
even
talking
choose
about.
any of these matrices, so you're gonna hit
That's all
enter. So there's matrix A, now hit X inverse. That's the inverse of A. Good. Now hit times, because we're gonna multiply it. Now go back to second matrix. Now go down to matrix B. That's just the name of matrix B. Now you just hit enter.
But you said for 1 year.
So that's it. That's the solution. So that means that the solution for X and Y is the matrix -2 and 1. So X is -2, Y is 1.
Pay for your bachelor's degree?
I pay for it regardless. We're gonna figure something out.
Yeah.
When I don't care if I have to get 2 jobs.
It's all posted on Canvas. I'll show you.
No, I mean,
You are available.
Yeah, I'll have to start it online. Because I don't know off the top of my head. I just go there and just read all my
I
classes.
did.
So take a look at about that.
Oh.
Here's my home. No, oh, I have to log in.
I spent like almost $200 on this thing.
Oh, wow.
So if you go into announcements
That's what
button,
happened to my boy.
and then it says, getting ready for
But
classes to
It's
begin,
just
maybe?
fine. I'm okay with it.
There's my office hours. So Monday, Wednesday, 10:30 to 12:15, Tuesday, Thursday. No?
I saw on your, so next to your office, outside your office area, and it's somebody who, I guess, is personal MAT 152 on Mondays and Wednesdays.
Yeah, that's for students in my 150 class.
Mm-hmm.
It would not be for this class.
Wait, what class is this?
213.
Oh.
No, this is 217.
Just kidding.
You're a good kidder.
So is
I know.
GBS 221 gonna be anything harder than this?
You know, Josue, I really try never to think about anything in terms of harder, but rather different. GBS 220 is a math class, and it is what,
221.
statistics?
No, 221.
Okay, yeah. Anyway, statistics, business statistics. So it's more math and it's more statistics, and it'll be about the same.
How come you don't teach those classes?
Technically, it's a business course, and you need a MBA. I have my degree is in math, not in business. It's a very subtle thing because the whole class is a math class. You think I can teach it?
Yeah, they
But-
require you to have this class.
Yeah.
Yeah. I have a question.
I'm glad, Simon. Questions are the doorway to wisdom.
Oh,
Okay, I'm gonna turn this off now.